morning, everyone. Okay, it's my pleasure to start the session today. And yeah, my name is Min, and I'm from the National University of Singapore. And I'm working on parallelizing on the stuff. And today I will introduce about our work on parallelizing EVM execution. So yeah, let's go into the details. So this is a very high-level overview of what this talk is about. Basically, we have GPUs are very powerful accelerators invented decades ago, mainly for gaming, but then it found its use cases in other domains as well. People have used it for general purpose computing, scientific computing, and recently AI picked up the trend. That's what make NVIDIA become the largest company in the world by market cap. So yeah, on our blockchain domain, we found its use case in mining, and you have seen like people use it for mining Ethereum for a long time before the merge. But then after the merge, a lot of compute power on all of those GPUs, like some of them come back to become AI training inference, but some of them find their new use case in ZK. So you have seen quite a few talks in this Devcon about accelerating prover, generating proof faster using GPU, but this talk is about something different. So we want to find, okay, those GPUs accelerator power, what can we use? What else can we use it for to help the Ethereum ecosystem? So we think about one more use case to beyond ZK to run the transactions in parallel. So nowadays, most of the transactions you can see is not just simple transfer from one account to another. So the transactions now are more complex smart contract executions. And those are quite compute intensive sometimes. That is also one of the reasons for people to set up like block limit and block scale limit so that the computation is bounded. So you can verify, run all the transaction in block time. And but we don't intend to use this work to like run your transaction in mainnet. We found another use case in fuzzing to secure smart contract. The use case we found from our work when we built our in-house fuzzing tool to find bugs in smart contract, we got the chance to run and test and also compare with state-of-the-art work in academia and also in industry. And we found that there's a very high demand to run transactions and test. And you get some feedback, you get some result. So you can, finally, the main goal is to find the bugs in smart contract to secure your application. And GPU is just the main, like, just the best, like, accelerator for you to run this kind of thing in this use case, because it has the massive parallel programming model. You can run like thousands of threads, and how about we map those thousands of threads into thousands of EVM instances run in parallel. So running transactions in parallel, first we focus on the niche fuzzing use case, but then along the way when we implement our project, we were approached by different teams, startups. They all building cool stuff, and some of them use some of our source code to fork out and have their own private repo with their own amazing use case in the ecosystem. But this talk will be mainly about fuzzing. I will have one slide about the other use case in the end. So what is fuzzing? Just a very simple, high-level understanding. Fuzzing, the main purpose is to find bugs in software. It's one of the popular techniques in software engineering. And recently, there's a trend for people to apply it to find bugs in your smart contracts as well. So this is a very high-level depiction of gray box fuzzing. Basically, you have a tool that generates a lot of inputs. Those inputs have more coverage and more complex than your unit test usually you use. So it's more complex, and eventually it's an iterative process. You generate input, you execute it, and then you get feedback. So those feedback can help the fuzzer to generate better input. Eventually, you can find the input that can trigger the bugs in your smart contract or in other software. So the inputs are so if you map it into Ethereum transaction to test smart contracts, the inputs are the states and transaction to interact with the app, your smart contract. And then the feedback can be traces, branching data, or the updated state after you run the transaction. And those are up to the fuzzing tool design and implementation. And yeah, so one example on the right is how they instrument the EVM to catch bugs. I just show very simple example. Some of them are not like the add overflow is not very it not exist anymore after Solidity 8 because they inject bytecode to check it before they try to revert it before the overflow happened. So for example, if you want to catch overflow, you just instrument the EVM to every time you see opcode add, you check the operand. If it's like over the 2 to the power of 256, then it's overflow. Yeah. Or another interesting opcode is jump I, all of your if-else condition in your smart contracts or require statement. It will be encoded into this jump I, and those will be the helpful hints for the fuzzing tool to further generate better input. I'll show one example of the run after this. So this is fuzzing on a conventional iterative process on your CPU. Then we try to map it into GPU execution. So you see, our fuzzer can generate thousands of input. Instead of iteratively one by one, now you can generate a bulk of them, like a batch of thousands of them, and then you can offload the execution of thousands of them into GPU. So this is the main idea, the main proposal in that our project trying to achieve. So after we offload the execution to GPU, we can map one or few threads in GPU to run this transaction, simulate the EVM, and then you get the feedback back to the fuzzer on the CPU and try to update it internal state strategy, generate better input. And yeah, that's about it. You have to you have to have some communication between the accelerator and the CPU side, and they all work together to find bugs in your smart contract. Okay, so we offload the EVM execution to GPU, and the EVM execution, basically you execute one transaction, and then you given the world state. So this is a very high level of what is running inside. So you see nowadays, like transaction interacting with smart contracts are quite complex. They have dynamic behavior. It's not just one single EVM call you run and you exit. It's actually every time you have a call context, and then each of them have the volatile machine states like stack memory, and they have their own size. And it's like evolve over like the running at the runtime. We don't know beforehand. So this is also one of the challenges when we try to implement on GPU. We cannot just pre-allocate the, for example, you know the stack size, maximum stack size and maximum column depth. If you pre-allocate everything, it's 6 gigabytes. And we don't need to do that at the beginning. So that is one of the challenges. And when you have call context, and then you can create a new call context, or you can revert back or exit and update the parent state, depending on the result of the child call. So these are the high level. And when we map to the GPU threads, actually we only consider each of the current call context. So when you enter a call context, you have your own stack memory, volatile machine states, and then if you enter the execution loop, basically you just keep fetching new opcode and increase program counter, executing the logic, and then eventually this call context either return back, revert exception, or create a new call context, and they keep looping. And then we have the decision of how many GPU threads that we can map to execute one EVM instance. And imagine we have to run thousands of them. So the decision is actually dependent on one of the library we use. We use a CGPN library from NVIDIA Lab to reduce the complexity of development at the moment. So they have the limitation like how many threads we can configure to compute one U into 56 arithmetic operation. So imagine it's like some big library that you can use out there. And yeah, and also because they have some limitations, so we are currently have a plan to develop our own library for this. They are developed for very general kind of use cases. You can configure the bit width, but then for our use case, you only need to use 256 uint. So yeah, we can optimize a bit more on this. So this is how you map the EVM to GPU threads. And after we implement mapping using those libraries, and you need to ensure it's correct. And for this one, when we developed this one, we didn't know much about the tools in the ecosystem. So thanks for the advice from Ethereum Foundation. We actually need to implement and compare with other EVM as well. So we integrate with Go EVM Lab, which is the tool developed by core developers of Ethereum, and then it's available there. And we make sure our traces are compatible with other EVM as well. Then we compare line by line. So we use EIP 3155, make sure it's output correct. And then we compare, and then we use ATH tests to compare. And then currently we pass on the test in functional folders at the important one. And the one I highlighted here are the ones that are most time consuming to us, recompile contracts and zero knowledge. They are just a few recompile contracts, but the logic and the time we spend on them is quite a lot. So yeah, EVM of course is simpler than this. And some of the things we can use open source, but some of them we have to develop on our own, especially EC pairing. Actually, we copy from the Python library from Ethereum. So we write it in CUDA. Based on the logic there. And so after all the tests, so rare corner cases remain, and mainly gas difference. So yeah, so if your fuzzing use case is not reliant, the logic not reliant on gas, termination, or some of the logic, then you can actually use it correctly. So we are still trying to fix all of the remaining gas difference. So after we are satisfied with the correctness, then we think about optimization. So because time is limited, our developing time, also the time of this talk, so I just pick one of the optimization that we did recently to show what we are doing. So basically, some of the, we try to optimize the normal transaction that you usually see out there in the real block and the real transaction. What are the popular, of course, what are the things that are critical to performance, what are the things that you have to execute all the time, so we optimize them first. So basically, we check the statistics, and then we found, okay, it's quite intuitive. It's quite obvious that the stack operations is almost everywhere. You have to optimize the stack first. And then after that, we also check the stats of the stack size. What is the normal stack size that usually transactions use? And what's the memory size? Then the program counter, it go up to 8,000. So we found that, okay, we cannot cache the program counter, it's too much. Cache the byte count, 8,000 bytes is too much. But then stack size 20 something, we can allocate the fixed size stack on fast memory. That's what we did. So we should pre-allocate that one first, very fast stack on share mem. And then after, if your stack is bigger than that, you can use a slower memory as well. So most of the transaction, you use this, you don't use a lot, you don't use large stack, then it will run very fast. That's one of the main optimization that we're trying to do. We try to optimize for conventional common transaction you can find out there. Okay, so current implementation, we are happy with one beta release currently. So basically, we support Shanghai. We started with Shanghai, but we couldn't catch up with new EVM hard fork. It's quite a lot of EIB implementations. So we stopped at Shanghai first, and then executable, we output the JSON trace, and then we have two versions, GPU, and we also have the share library, so you can use it in two modes. One is you use this share library, it's open source now, and then you can use it to try on Google collaboration, the Google Colab, you can use GPU there. So yeah, you can use it in two modes. You can write your Python code to interact with it, and also you can use the executable. Yeah. So performance is still depending on the workload. So it requires more comprehensive benchmarking. But yeah, we compare with our own CPU version, it's faster. But one thing is that our CPU version is actually slower than the current EVM implementation out there. So it's not like directly apple to apple comparison. And yeah, we are still improving the performance. Yeah, so this is one of the sample run in fuzzing and real, like in action. So you can try on Google Colab, the link in our GitHub repo. And then one example is a toy example in smart contracts with some of the very obvious bug there and some of the input guarding like if conditions. So to make sure that you do some real fuzzing, you make sure you get the correct input. You can run it and eventually it will like output the line, the source code line, and the inputs that trigger the bug. Like you see input equal 400,000 or some, 40,000 for input 4, 5, 6, 7 and trigger the bug. It can show you the source code, the line of bug. This one running, the execution running in GPU. So besides the detecting bug, we also have feedback. So these are feedback branching feedback. One example is this function test branch. It's like there's a condition for input to be 1 million, and you see the current input and the distance before you can break that branch. Those are the gray box fuzzer technique that we implement in here. Those are quite common in gray box fuzzer fuzzing tools out there. And our current release, the bottleneck still remains in the way we prepare transaction and we get back the serialized data to update the state of our fuzzing tool. So it's still slow. But we have experimental branch where we remove all of the complex logic. And of course, this branch does not conform with the yellow paper anymore, but then it will reach very high throughput. It can reach like 60K transactions per second and improving. And we saw some teams have private repo, and some of them clone or fork from our repo with like private implementation on optimization. They can reach 100,000 of transactions per second as well. But we are open source, and we're trying to make sure it's still conform with the Ethereum standard. And beyond fuzzing, this is some of the interesting use case where we talk with other teams, other team doing cool stuff out there, but they are doing the layer 2 and also fuzzing. But the main thing when we were thinking about parallelized transactions for Ethereum execution client, is it possible? It sounds cool, but then it's not very practical at the moment, because you need more transactions. Currently, how many? Like hundreds? You need thousands to have like to exploit that parallelism in GPU, and also The transactions, they are all different. They are not very similar, so it's not easy to achieve speed up on GPU. And also, to achieve this kind of thing, you need more client support. Like the GPU memory, you cannot just get that terabyte of word state. It's not possible. It's in the minute. It's too big to run. And also, because of memory constraint, and also the client needs to ensure it's safe and correct to run those transactions in parallel, which is not. Because transaction, you need to run sequentially to one by one after the other, and eventually to get the final state. This one run in parallel. You have to make sure that all the nodes running it reach the same deterministic output so they can reach consensus. Otherwise, it's not possible at all. So that's what we think at the moment. So we still can find other use cases besides like trying to speed up Ethereum execution client. We see other layer 2 teams also can try to have their own execution engine. Also, transaction simulation platform. I saw like people use it to simulate swap, for example. And imagine you have a lot of similar transaction testing simulations. And this one is a use case for it. Yeah. You can simulate millions of swap in a short time, serving a lot of users. Yeah. Okay, so the last 2 slides, I want to talk about our team and collaborators. So yeah, working with me. We have a small team of 3 researchers and engineers. Working with me is Chung Lee, and we are from the Singapore Blockchain Innovation Programs. NUS. Also working with me was Dan, and we worked in Singapore before, and he went back to Romania to become professor. And yeah, we want to thank Frederick and Ethereum Foundation for the advices and the grant support, especially the advices to make sure it's correct and how to use all of the new tools in the ecosystem that we were not really familiar with. Thank you. Yeah, so that's all about this one, and you can find out on the GitHub. And yeah, just feel free to create PR, open issues, discussions, and reach out to me. I will try to help.
Thank you, Min, and thank you for this amazing presentation. So I have a few questions. Let's go through them. Let's take the first one. How much work would it take to integrate this in an open source fuzzer like Echidna?
Yeah, you can use it. Currently, we release the shared library. You can use it right away. But the thing is, you need to modify your fuzzer. Our example toy fuzzer, we have that bottleneck to repair thousands of transactions before you send to GPU. That one is quite a big bottleneck. You run it on GPU, it's fast, but then you prepare for it, and you run, you collect the result, it's still quite bad. So currently, we need time to like improve the interaction between the library and your fuzzing tool.
So it works, but you need to work on piping.
Yeah, the right? Interaction, yeah.
Okay, on plumbing. All right. Can QVM plug into a simulated node tool like Anvil or Eve Tester?
Yeah, so in the end, we need to make sure it's possible, but we need to make sure it's compatible for API calls. So basically, we provide that library. If you have your own adapter, your requirements, so you just send us the state and the transaction you want to run, but should make sure the state is not so big. We can manageable, like transfer it to CPU and keep it there. Sorry, GPU memory and keep it there. And it's possible to transfer the state transaction, run and return it back the result, whatever result format that you want.
Fantastic, thank you. All right, third question. Would fuzzers have to change to adapt to your GPU acceleration? It seems like this is a different version of the same question. Let's mark it as answered. All right, fourth question. How does the GPU thread get the state from when executing sload? Well, that's specific.
Okay.
You want to take the next one?
So we have the data structure and reside on global memory. So for the states and memory, we have to keep it in the slow memory. We don't do any caching. And that one, we keep the structure pointing to the state, and we search through that. So basically, if the state is big, So this is one implementation detail. We didn't implement very fast searching in the states. Basically, we have to go through on the array of accounts. So if the state is so big, currently it's quite slow. But yeah, that's how it works. So everything on global memory, we have to search through them.
Fantastic, thank you. All right, we still have 10 seconds, so maybe a more playful question. Have you considered calling it cute VM rather than QVM? QEVM?
I don't know.
But, you know, suggestions, you know?
Yeah, we might change it to this theme.
Wonderful. I mean, thank you for your time and all the work you obviously put in your slide. And looking forward to your work.
Yeah, thank you.
All right, friends, we'll be back in 5 minutes with our next speaker, Valentine from East Zurich. Stick around, he has plenty of really cool stuff to share. And we're back on. All right, people. Next speaker is Valentine from ETH Zurich. ETH Zurich is not an Ethereum organization. It's a leading university in Switzerland. So Valentine is going to talk to us about fuzzing infrastructure. Get ready to get your mind blown. And like for the previous session, scan the QR code who's going to appear here to ask your questions, and I'll make sure to ask the best ones at the end of the session. Also make sure to read the questions that other people have asked, because you can upvote them, and the questions that have the most upvotes will be treated first. All right, Valentine, please come in. Welcome.
Good morning, everyone. So today I'll talk about fuzzing for zero-knowledge infrastructure, and this is joint work with my collaborators from the Technical University of Vienna. So just to kind of make sure we are all on the same page, let's have a short definition of what I understand by zero-knowledge infrastructure. So for this talk, I'll define zero-knowledge infrastructure as software components that are used for compiling, executing, proving, and verifying ZK circuits. So examples would be the processing pipelines that are commonly used by DSLs for describing ZK circuits, or maybe in the future we'll also look at entire ZK EVMs. So with this out of the way, let's look at why this is an important topic and why more people should be doing this. Well, first, zero-knowledge infrastructure is highly complex and highly critical. For instance, it's used in several L2 chains, so kind of bugs there could have catastrophic financial and reputational impact, and we should really make sure these components are as bulletproof as they can get. While we haven't seen a really catastrophic incident in this field, maybe perhaps comparable to the DAO hack in 2016, it's really important that we have rigorous testing for these components, and we use the best engineering discipline that we can have, right? Because these components are really complex, and getting them right is not easy. So what is fuzzing? I don't think I have to explain this after the last talk, but fuzzing is widely used in industry. For instance, at Microsoft, Google, Meta, they're fuzzing a lot of their infrastructure to catch bugs before hackers can actually exploit them in practice. So in this talk, I'll give you an overview of our fuzzer for finding critical bugs in processing pipelines for zero-knowledge circuits. The fuzzer is called Circus, and it already supports 4 of these pipelines, namely Circum, Corsair, Gnark, and Noir. And there's, like a gazillion of different DSLs popping up, it seems. Like you walk around here and you see another one in the corner. And we've already found 16 bugs in total for the 4 pipelines we looked at. 15 have already been fixed, so that kind of shows that these bugs are really taken seriously, and developers sometimes respond within hours to actually get them fixed. You can also see a kind of breakdown of the different bugs and where we found them. And as you can see, they're kind of very evenly spread across the different pipelines, so it's not like there's one pipeline that's responsible for all the bugs that we found. Now, kind of to make sure that everybody understands, I assume not all people are aware of what these processing pipelines look like. Here's a short kind of summary. You can see in the sort of yellow box, there's a circuit that the user writes that goes into the compiler, and then the compiler hands some output to the witness generator, and the witness generator can then take the input, so the user input to the circuit, and generate a witness that can be then used by the prover, and then the prover generates a proof that can then be verified to essentially check that the circuit was actually executed. So now that we have a bit of an understanding of how these pipelines look like, let's dive a bit deeper to understand how we find these bugs. So first, I want to be very clear. We are not cryptographers. This is not my background. My background is in software security, program analysis. And for this reason, I can't really try to understand the logic that's in the intricate logic in many of these components, which is why we treat these essentially as a black box. So much like what a typical user would do, we just view them as a black box. So how can we still find all these bugs, right? Well, first, we have a lot of experience in testing complex software for complex domains and building fuzzers for them. So we've done quite a bit of work on fuzzing for smart contracts. It's probably the work that's most closely to the audience that's here. And for instance, we created the Harvey fuzzer many years ago, and we're still kind of maintaining it. We also did some work on ML models and on testing ML models and testing program analysis tools. If you want to know more, check out the papers that are online. And the second reason why we were able to find these bugs is that we have a not-so-secret weapon, which is called metamorphic testing. So before explaining in a bit more detail what metamorphic testing is, let me just give you kind of a short summary of how we got here, how we got into this, interested in this topic. So we were, as I said, we were working on fuzzing for smart contracts mainly for many years. And then at some point, I guess maybe like a year ago roughly, Consensus, they released the Linea blockchain. That is one of the first ZK EVMs. And we were like, well, this is really complex. We started looking into it a bit. And we saw that there are these components like the Gnark library and the Corsair language for processing zero-knowledge circuits. So we were like, oh, what can we do to, test these? What can we do to make sure that there are no bugs in these components? And that's when we started building kind of a predecessor to this fuzzer I'm presenting today, which is called Rio. So the Rio is a fuzzer for the Gnark library specifically. And then essentially this Circus fuzzer I'm presenting today is essentially an evolution of this fuzzer that is a bit more general and can target multiple DSLs. All right, now back to metamorphic testing. So what is metamorphic testing? I think the shortest way to summarize it, it's kind of a way to define test oracles in a pretty elegant and concise way. So to illustrate, I've collected a few examples that explain this and try to explain what metamorphic testing is. So the first example is how to actually test that the sorting function sort for an input, let's say an array of integers x, actually does the right thing. Well, there's many ways to check this, but here's a way to check it using metamorphic testing. So you sort the input x, and then you also sort x, but you shuffle it randomly, right? And these two, the output of both of these invocations of the function, they should have the same output, right? So pretty nice and concise specification. So let's look at another example. Here, we want to test essentially some procedure for computing the shortest path in graph G between the nodes N and M. So how can we do this with metamorphic testing? Well, one way to do it is to say, the shortest path between N and M in the graph G is less than the shortest path between N and M in the graph where we take G, but we remove some random edge, right? Because that edge might have been on the shortest path, and then the shortest path could become longer, right? So we can also apply the same kind of principle to more complex components, like an entire compiler, right? So here's an example of how to do this with metamorphic testing. When you take a program P and you compile it and then run it, you should essentially see the same behavior as when you take the program P, but you add some dead code somewhere randomly, right? And you compile it and you run it. Shouldn't matter, right? Should give you the same output, essentially. So with this, let's look at how we can apply kind of the same reasoning principle to zero-knowledge circuits. So the fuzzer, what it does is it first generates a random circuit, C1, and then it applies a random transformation to C1 to get a new circuit, C2. So now we have two circuits that are essentially syntactically perhaps completely different, but semantically they should have the same behavior. And now the fuzzer generates an input I and invokes the processing pipelines for both of these circuits. And if there's any difference in the output or the behavior, then that's a bug somewhere in this processing pipeline. So for instance, for one circuit, we might not be able to generate a witness, but for the other one, we would. Then there's probably a bug somewhere in the compiler or in the witness generator. So let's look at a few of these transformations. to kind of understand how the fuzzer does this. So here's a very simple transformation. If you have somewhere in your circuit an expression E, you can always apply, you can always multiply the expression by 1, right? That should not change anything. Or you can also divide by 1. Again, shouldn't have any effect on the circuits. Another transformation is to basically negate the expression E twice. Or you can also apply other transformations, like swapping the two operands of a multiplication. And then we also have some transformations that use essentially new randomly generated expressions. So here, for instance, we replace an expression E with E minus some random expression plus some random expression, right? That should, again, not have any effect. And we have a small DSL for describing these circuits, so there's many more of these transformations. So currently we support roughly 90 such rules, but you can easily add more of them and think of new ones if you like to. So we also found a number of bugs in the different pipelines, and let's look at a few of them just to kind of give you the idea and give you a concrete example that you can look at. So here on the left, we see a small example circuit in the Circum language. You can also look up the GitHub issue if you'd like to. But this is essentially a minimized, cleaned up version of the circuit. And as you can see, there's a variable p. In practice, this is essentially just a constant. It just didn't fit on the slide, so I put it at the bottom. But think of p just as a normal constant in your program. And now what the fuzzer does is it generates a transformation of this circuit, which is the one that's shown on the right. And here, it applies a number of metamorphic transformations. So for instance, it seems like the fuzzer first multiplied the expression p by 1, then subtracted 0 from 1, and then divided that expression by 1. And when we execute this, when we execute these two circuits, we can see that that the output, out1 and out2, actually are not the same. So this is bad, and this was a bug that we found. It seemed like there was a bug in the witness generation part. And here's another bug that we found in Gnark. So at the top, you can again see the original circuit that the fuzzer generated. And then we can also see the transformed circuit where the fuzzer essentially changed the expression 0 to just 0 or 0, which should be equivalent, right? And here we observed that for C1, there was no witness that was generated, whereas for C2, there was. So this, again, is a bug somewhere in this pipeline. And yeah, now that you've kind of hopefully got an overview of the tool and saw a bit how these bugs look like in practice, I hope more people will, start looking into this problem because I think it's a very important problem. We need to really make sure that these components are bulletproof because otherwise, pretty bad things can happen. It's better to do this before some attacker does it, right? And you don't need to be a cryptographer to actually find these bugs. So, that gives us a lot more people that can actually look into this. Because I think so far we only really scratched the surface. So there's more things that need to be done to test these components. Also, there's components like this popping up every now and then. So we really need to make sure they're safe. And we also should do continuous fuzzing of all these components. So for the Gnark team, we actually implemented a continuous fuzzing setup where whenever they commit the latest version to master, we start a new fuzzing campaign. We run for 24 hours. We tell them if something is wrong, and then the next day, same thing happens. We're also planning to do the same for Corsair, and if you're interested in, us taking a look at your ZK infrastructure, please reach out. And if you want to know more about what's going on in the fuzzer, then please also check out our paper. You can scan the QR code there if you want to take a look. Yeah.
Fantastic. Thank you, Valentin, for this presentation. Let's get to the questions, shall we?
Yeah.
All right. So I've sorted the questions. Again, you have a QR code here. You can ask your questions, and I'll ask the ones that are the most upvoted. So let's go to the first one. When you identify a bug, can you just say, hey, there's a bug, or do you provide a path to fix it? Like, do you identify where the bug exists within the circuit?
We don't directly identify where the bug is, but when we generate the test inputs, like the circuits, we try to minimize them. So we try to keep them as small as possible, so the developers can really, hopefully, quite easily identify where things go wrong. And yeah, so far, I think the developers are very happy with the bugs reported, and I think there was no issues finding the bug once they had the input.
Makes sense. Thank you. Second question. Do you fuzz logical expressions? They're encoding in circuits?
Yeah, we do. I think, yeah, so for instance, we apply some common transformations, like applying De Morgan's rule and so on. So there's a bunch of these transformations that we use in the fuzzer.
Wonderful. Third, where's the bug nest? Where do bugs usually reside in your historical fuzzing, like from what you've seen?
I think it's hard to like.
Can you really derive enough data from? You found 17. Right?
Yeah. I think it's probably too early to say, but we did observe that the fuzzer found bugs basically in different components. So we found bugs in the compilers. We found bugs in the witness generator. We found bugs in the prover as well. I don't think we found bugs in the verifier. It seems like, yeah, that's kind of towards the end of the pipeline. And I think many people are, very concerned about getting the verifier right. So maybe that's also paying off here. But we'll keep trying. We'll see.
Nice. Okay. When Cairo fuzzing?
Yeah,
I guess you answered it in your slide. If we're interested, people can talk to you.
Exactly.
And so
if
Cairo
somebody from Starkware wants to, us to look at more at Cairo, then yeah, please reach out. We're interested. It's definitely a good idea to do that. Yeah.
Wonderful. Well, I'll reach out. What do you think of concolic testing of ZK circuits? I had to ask ChatGPT what concolic testing is, and I still don't understand it.
Okay. Yeah, so concolic testing, essentially, I mean, for the audience, maybe it's essentially a way to, generate new inputs by doing some kind of symbolic execution. But basically, for some expressions, that might be really complex. Like you have non-linear expressions in these circuits. So there you might want to concretize some inputs, and that's the concolic part. So it's like concrete and symbolic. But yeah, so I think that's an interesting area. It's not sort of what we focused on because we're not so much interested in actually generating inputs for these circuits. That's something you would probably want to do if you want to have a specific circuit that you want to get right, and you want to make sure it satisfies some properties. Then you probably should think about concolic testing for that circuit. Yeah.
Perfect. Thank you. How does it feel to find a bug? Like literally, when you find one, is it scary? Is it exciting? I mean, you're looking for those, so it's probably a bit exciting, but it's also scary. There's probably money on the line. How does it feel?
No, it's definitely exciting, and I work a lot with students. and it really, you can see they're excited when they find a bug. They're happy they're making an impact. And also the reactions from the developers are a great motivation to find more bugs, because usually they're very, they have been very positive.
I don't believe you. There's no way you go to people and say, oh, I broke your shit. And they're like, oh yeah, amazing.
Yeah. I mean, if you're sort of, if you're, an L2 and one bug like this can, wreck your system, then, in some sense, your job is also on the line. So you should.
You want to find those bugs. I'm not saying you don't want to. It's just scary. Yeah. But when I think about bugs, I think like, yes, I want to fix them. But the first thing that comes to mind is like, oh yes, no. But you're right. It's better to be aware of first than not. Okay, we can actually take the last. 1 second left. Let's wrap it up, or do you want to? Are you using property-based testing for choosing the input?
I mean, you can call it property-based testing. We're generating the inputs right now completely randomly, so it's kind of black box fuzzing that we're doing. And we're also considering to do more, feedback-directed fuzzing, like you saw in the last talk.
Fantastic. Thank you, Valentin.
Thank you.
Oops, I'm not used to the MC flow yet. All right, I see more people are joining in. Welcome. We still have a bunch of really cool sessions coming up. We'll be back in 5 minutes. right, next session is starting, people. So for the next session, again, don't forget, there will be a QR code here. Ask your question there. Upvote the questions of your friend, and we'll be able to ask all of our questions to Stefanos at the end of his presentation. Stefanos is a PhD student at Imperial College in London. He's also a part of ZK Security, doing research in the zero-knowledge field, and today he will talk about what we don't know about ZK. Please welcome Stefanos.
Hello, thanks for the introduction. So today I'm going to talk about vulnerabilities, mainly in the implementation of snarks or ZK snarks, and also on what can go wrong when we deploy snarks in production. This is a joint work with collaborators from TUM, the Ethereum Foundation, ZK Security, the Scroll Foundation, and also Imperial College London. Okay, so let's start. Okay, what is the state of ZKP applications today? We have ZK rollups that have become very popular in the last 2 years. They have more than 5 billion USD in TVL in them. We have Zcash, which is a payment system. It was deployed, I think, the first version around 2015, 2016. We have many ZK applications, both for infrastructure, such as ZK bridges, but also for private payments, for using wallets without having to use seed phrases like ZK login. We have private programmable L1s and L2s like Mina, Aleo, Aztec, and also we have some off-chain applications. And although all of those systems have been deployed, we haven't seen any major exploits like the DAO exploit we had in smart contracts. And although we haven't seen any exploit, there have been bugs in systems deployed in production. So Zcash had a vulnerability. Sorry for the pictures, might be a bit small, but I will go through them. So Zcash had a vulnerability for, I think, more than a year in it. People from within the Zcash found it and patched it. Then one of the most popular mixers had a vulnerability that if someone exploited, it could have basically drained the smart contracts of that protocol. One of the most popular ZK rollups had a major vulnerability that someone could again potentially could have exploited and get everything out of that rollup. And also I would say that in audits in ZK protocols, even in top-notch protocols, if you compare it with top-notch smart contract protocols, the ratio of critical vulnerabilities is even higher. So there are many vulnerabilities, and people for many years suggested that ZKPs are very difficult and very hard, and not many people actually understand them. And also they have suggested that to exploit a ZK protocol, it's much more difficult to exploit, for example, a smart contract vulnerability. I would say the first one is not true anymore. Right? Because if you see the number of presentations in ZK in Devcon this year and compared with 3 years ago, we have an exponential increase. And also, although it might be true that some ZK vulnerabilities is difficult to exploit, I would say that some of them are pretty simple. And for example, here we have a Circum circuit. It's a very old circuit, but anyone who has written a Circum circuit could probably understand what's going on here, and still there are such vulnerabilities in ZK protocols that I think are pretty easy to exploit. So there is a huge risk if there are still vulnerabilities in deployed protocols to be able to exploit them at some point. Okay, so let's start with explaining what are the properties of a ZK protocol, right? We have knowledge soundness, which basically means that a dishonest prover cannot convince a verifier of an invalid statement, except with a negligible probability. We have perfect completeness, which means that if you have a valid statement, a prover will always be able to convince an honest verifier of the correctness of that statement. And also we have zero knowledge, which means that the proof pi that we produce with the zero knowledge proof does not reveal anything about the witness we are proving. So what is our threat model in ZK world, right? We have three adversaries. We have the network adversary, who observe the system and its public values, but cannot interact with the system. We have the adversarial user, which basically is able to submit some inputs for proof generation in a honest and non-malicious prover. And finally, we have the adversarial prover, which is the most common threat model. And it's our threat model when we actually need the ZK property, right? But I would argue that even if we don't need it, if we want to have a fully permissionless system, then that's the adversary we have. And has the ability to produce proofs and has the ability basically to do everything to try to trick the verifier. To give you an example of what I mean with the second category, because it might be a bit confusing, consider ZK rollups at the moment, right? Where we have a single centralized trusted L2 node that is both the sequencer and the prover. So users can only submit their transactions there, and then that centralized node will produce a proof. So in that case, we have an adversarial user, basically. And what can be the impact of ZK vulnerabilities? So we might be able to try to break soundness, which means that a prover can convince a verifier of a false statement, and that could result in basically, for example, in ZK rollup, to get all the funds out of it. We can break completeness, which means that a verifier cannot verify proofs, or basically that the prover might generate invalid proofs, right? And for example, such a vulnerability could basically have a high impact in the liveness of ZK rollups, and we might also break zero knowledge, which means we have some information leakage. Okay, so what we did is we analyzed 141 bugs and vulnerabilities from audit reports, from vulnerability disclosures, and from bug trackers. And our goal was to split those vulnerabilities in layers and understand what can go wrong in each layer, and also create a taxonomy of vulnerabilities. So let's start with that figure. So in the real work, non-snark work, we'll have a relation, a specification, some idea that we want to actually create a ZKPA about it. And we might have some public and private inputs. So the first step is to manually encode that specification, that idea, in a circuit and get the circuit implementation. So we figure out that in that level, it's where most of the vulnerabilities happen. And the main reason, in our understanding, is because it's confusing for most developers to write circuits, because they have to think both about computation and also about constraints. And they might do very aggressive optimizations there, and they might try to apply some tricks, and that typically leads to vulnerabilities. So we identified three main vulnerabilities. Under-constrained vulnerabilities, which means that you forgot some constraints, or some of your variables are partially constrained. We might have, and that typically leads to soundness vulnerabilities, which is the worst vulnerability that can happen in the ZK system. Then we have over-constrained vulnerabilities, which is the exact opposite. That most typically will lead to completeness issues. And we also have computation or hint errors, which is just on the computation part. And accordingly, you might have messed up constraints, but the root cause was in the computation part. So we did a complete root cause analysis. And I will share with you a QR code for our paper to look into examples and to look on how you can fix some of those vulnerabilities, etc. But very briefly here, we have categorized them in three main root cause classes. First is that when developing circuits, we have a different programming model, and that could lead to many vulnerabilities. Secondly, we observed that the root cause of vulnerabilities were optimizations, and also having cryptography at the outer layer and in very low-level DSLs that could introduce many vulnerabilities. and also common errors like in any software, like specification issues or API misuses, etc. So the next layer is the front end, which is basically composed from two components, a compiler and a witness generator. The compiler will take the circuit and will try to produce an intermediate representation that it's on what our proof system works on top, for example, R1CS. And then the witness generator will take the circuit, will take the public and the private variables we have, and it will produce a witness. And the next one is a backend. The backend is composed of three main functions: setup, proving, and verification, and things can go wrong in all those functions. So the vulnerabilities we identified here in the front end is incorrect constraint compilation and errors in witness generation. And in the previous presentation, we saw how things can go bad there. And it's very critical to actually trust and be able to have correct implementations of frontends. And in the backend, the situation is quite similar. From our data, we found out that unsafe verifier, it's a very common issue and can lead to major vulnerabilities. Let's go to the next one. The next one and the last one, it's the integration layer, which is basically, you can think of it in the blockchain space as the JavaScript that is responsible to run your prover client side and create the proof, and also the smart contract that consumes that proof and calls the verifier you have implemented or it was produced automatically and try to do some things. And we had some very interesting vulnerabilities in that layer. I want to focus in the first one, which is passing unchecked data. And what does that mean? Sometimes, as already said, we might try to do some optimizations in the circuits. And for example, one thing that it's pretty common is for people to say, okay, in that circuit, let's have some implicit assumptions that our inputs are in a specific range, and then delegate that check to the actual code that will call the verifier. So in that example, we forgot to do such a check, and that could lead to major vulnerabilities then in our infrastructure. And in the last year or so, there has been a major change in some architectures where instead of circuits, we have ZKVM circuits, right? So the developers now only care about writing some program, typically in a high-level language like Rust, and then compile that program and giving it as an input to ZKVM. Still, circuit bugs can happen in the ZKVM itself, and I would say a subtle new threat here is traditional compilation errors that might happen to the Rust compiler, for example. That could lead to have invalid proofs. So that's something that people should take into consideration when using ZKVMs also. So another way to see what we currently described is in a hierarchical way. And here I have an example of all the stack when we use the Circum programming languages and Slang.js with Growth 16 Azure Proof System. I have two new layers here. One is field arithmetic elliptic curves, which have nothing to do with ZK, but when we construct and implement a proof system, we have to have such a very efficient library, and things can go wrong there. And also things can go wrong in the hardware, in the operating system, in the blockchain we are using, right? So you should always be very, basically think about what you are going to use and apply all traditional best security practices we know from other fields. And one last thing is that in the proof system, there could be errors there, there could be errors in the initial description, in the papers of proof systems. So if something goes wrong there, it doesn't matter if you have formally verified Circum circuits, if you have the best backend or frontend, it could be exploitable. And that basically it's true for any layer. So if your front-end or the back-end it's vulnerable, then even if you have formally verified your circuits, they could be exploitable. Okay, so we did that analysis, and now I want to present some of the results. So we categorized the bugs in all those layers and also based on their impacts. And we can see that circuits was the #1 threat in the whole infrastructure of using ZKPs. And also most of the vulnerabilities are, can result in soundness issues. So what can we do? Fortunately, there has been like a lot of development and a lot of research of creating security tools for ZK circuits, specifically for ZK VMs or ZK EVMs, and also in the last month, 2 new papers were published and tools, Circus, which was presented in the previous talk, and also MTZK, which is great because such novel tools can detect infrastructure bugs in circuits, in ZKPs, but I would say there are still a lot of work that needs to be done. For example, most of the circuit tools, they target a specific DSL, and also they typically target a specific vulnerability class. And then we have some tools like static analysis tools like Circum, which might have tons of false positives. And then we have some really nice tools and very novel tools like Picus that try to formally verify and find any under constraint issues in the circuits, but unfortunately those tools do not scale that well. So there's a lot of space to have innovation and try to build better tools. And here I have a list of security tools. You can scan that QR code, and it's basically GitHub repository. If I don't have any of the tools that you know of, please add them. And yeah, we need to do a better job here. And one also major issue I see in the space is that we don't have good tools for writing tests. And most of the code base that use zero knowledge proofs are unfortunately not that good into having like complete test suites and try to understand in the testing part both soundness and completeness issues. Okay, so in conclusion, why do we have bugs? One of the reasons is that because ZKPs are not just mods. There are implementations, and many things can go wrong in those implementations. Why else? This is a quote from Ron Rivest in a completely different context, but I really like it. And I would say that in the ZK space, unfortunately, we have given to the poor developer enough rope with which to hang himself. Circuit languages are typically very low level, so they don't have good abstractions for developers to write safe code. We expose a lot of cryptography to the outer layers, and also there is a lot of complexity and a different threat model than what developers are used to. And there is a lack of specification throughout the whole infrastructure and the whole stack for using ZKPs, so we need to write more specifications. So what can we do? Basically, we have to negate everything from the previous slide. We need more layering resources, which I think we are doing a great job in that as a community. We need to write specifications and get used to write specifications, because if we have complete specification, then we know exactly what checks we should put in each layer and what vulnerabilities can happen in each layer, and that's how we can help developers, but also auditors into doing a better job in trying to find vulnerabilities in those systems. We need easier and more secure programming languages, which I think it's kind of where we are heading to. For example, Noir is a great language that it's much more safer than writing circuits in Circum or Hello 2. But in some cases, people will still need to write circuits in Hello 2 or Circum because they need to do some specific optimizations or they need to deploy to specific blockchains, for example. And then we need better testing and security tooling, from simple frameworks to write unit tests, to do property-based testing, to formal verification, and not just formal verification. So that's it. I have there a link with our paper where you can find many examples and how to try to avoid some of those pitfalls. And we also have a blog post that we publish many blogs about ZK security in general. So thanks a lot.
Thank you, Stefanos. This was enlightening. All right, people. As usual, you can ask your questions here. We're going to go through them in order. And let's take the first one. Several times in your slides, you referred to witnesses. What are witnesses? Are those private inputs?
So a witness, I would say, it's composed from both the private inputs, the public inputs, and all the intermediate steps, and the outputs for our circuit. So I will say it's a trace that then we create a proof about that trace.
Thank you. All right, next question. I've put a bunch of those, so do ask serious questions, please. We have a bit of time. What is your favorite bug ever? What is the most interesting bug you've ever found?
That's a very good question. I think I can't pick one, but I would say typically the simple bugs, right? For example, the bug I have in one of the first slides, that could have led to basically draining one of the major mixers we have in the space. But also bugs that have to do with using cryptography in the circuits, and typically due to some optimizations or some logic errors in those circuits, there could be like pretty interesting exploits that someone can do.
Pretty cool, thank you. All right, the next one. You're doing research, looking for bugs, you're paying your bills and buying your foods by finding bugs. Can we consider you have a bug-based diet?
We can consider that, yeah, nice. Definitely. I hope that in some future world there won't be that many bugs, and maybe I will have a better diet. But unfortunately, at the moment, we have tons of bugs.
Fantastic, thank you. What are your thoughts on tea?
Okay, that's the question of Devcon SEA. Everyone asking that question. I would say it's a different. You have different security assumptions when you use TEs, right? I think it can work along with ZKPs, but they can't replace ZKPs. You have a much weaker threat model when you are working with TEs. So yeah, people should use them when they have to use them, but also don't trust them like a black box that will do everything for you and you are secure if you use a TE.
Wonderful, thank you. What can we do to make more secure languages like Noir faster compared to Circum, particularly with respect to gas cost? How do we make it more efficient?
So gas cost, I will say that it's independent kind of what programming language you're using. It's more about like what proof system you are using, right? And if that proof system has very efficient verification, that's the main factor. But also more general in the circuit layer, I would say that indeed someone, if you don't like really use unsafe in Noir, which then breaks the whole purpose of using Noir, you can write more optimized circuits at that point in Circum. But I would hope that we will have major advances in compilers for ZKPs, and then we can have like compiler optimizations that are very strong, like in any other field, and rely on those optimizations to get like pretty optimized circuits. But if we do that, then we need very, very solid testing for our compilers to detect any issues in those optimizations.
Thank you. You mentioned in your slide that sometimes we give too much rope to the users to hang themselves with. I think that designing ZK circuits is difficult, but also using them is not very commonplace, right? A lot of users are not used to using this kind of systems and what goes in, what goes out, what you can do with them, what is safe behavior to do that. You mentioned learning resources. Do you think there's something to do with users also to explain to them what are the benefits and what should be done, or is it entirely on the app developer?
Yeah. That's a great question. I think as researchers, it's our responsibility to create learning resources that are easy to follow by almost everyone. So I think we are doing kind of a good job there. For example, at ZK Security, we published a book on Hello 2, and basically many teams in that space develop pretty nice learning resources. And what I really like is that they also have a section about security vulnerabilities and what you should look at when you use a specific DSL. So yeah, I think we are doing a great job on that. And in the few years, it will be even better.
Fantastic. Stefanos, thank you. We're over time. So thank you for your talk.
Thank you. Thanks a lot.
All right. We'll be back in 5 minutes with Pratyush. Stick around. It's going to be interesting. So I'm just here to announce a small delay. Unfortunately, we have zero knowledge on the whereabouts of the next speaker. With the rain outside, it's possible that the street circuit was overflowed. I don't have a third one. We're waiting for him. We'll be back. We're going to wait for 5 more minutes, and hopefully he'll show up and be able to present. Please wait a little bit again. The next speaker is not available, unfortunately, so the session is cancelled. The next session will happen in 20 minutes at 12. In the meanwhile, stay here, grab a coffee, enjoy the relaxing mood, and have a good time. No mic? No mic? I can't hear people. I'm sure people. Can you wait? Oh, wait, you can hear me. Sorry. Hey, and we're back. Welcome, everyone. Thank you for showing up to this next session. The next session will be with Richard. So Richard didn't put a bio on the Devcon website, so I can't tell you much about it, but a picture is worth 1,000 words. Go look up his picture. He's with a deer, so it's funny. But Richard will talk to us about the Ethers.js API, its hidden gem, and how you can make the most of using this specific library. So open your ears, learn a ton of stuff, and ask questions. There's going to be a QR code here. You can ask all the questions you want during the presentation. We'll cover them at the end of the presentation. And you can also upvote the questions that you like to make sure that they get covered by Richard. All right, Richard, welcome.
Okay. Thanks. Sorry, I totally thought I had a bio up, but for those that don't know me, my name is Richard. I work on Ethers.js. Oh, there's multiple red X's. Which red X? Okay, this one. Okay, sorry. Hi, so I'm Richard. I work on Ethers.js. I'll try to face this one so I can talk to you, but I'll turn around. Hello all. So Ethers.js is a open source library for dealing with Ethereum. I'm guessing a lot of people here probably already use it. If not, welcome, and I hope you can try out some of these new things that I feel are like when I tell people these things, the common phrase is, I did not know you could do that, and then, awesome. So I'll just start, and so there's different types of providers, so I'll go into a few things first. So first of all, the multi-call provider, for those that are familiar with like multi-call, this is based on like kind of abusing how init transactions work. So there's actually no contract on chain. It works if you're using hard hat on a pristine chain. You don't need anything deployed. It just works. I'll cover in a second how that works. But as you can, yeah, I'm going to turn around. Sorry. Anyways, you can see, so you have to pull in the Ethers extension package. You wrap your provider in a multi-call provider, and this will make sure that all the ETH calls you send kind of get wrapped up and like sandwiched into this weird compiled solidity thing, so that when you actually make the calls, they get sent off in parallel as one ETH call, and it gets wrapped up in the multi-call contract. I'm assuming is everyone here familiar with multi-calls? I feel like yes. Okay, perfect. The one problem with like multi-calls in general is like if you do a wait on each ETH call, it can't batch those together. So you do have to like kind of smush them all together in this really annoying way in how JavaScript deals with await, async. If you'll have like a good solution to this, I'd love to hear that too. So one thing to keep in mind with multi-calls that in this work, this is true for all multi-calls, like message.sender is wrong. Usually that doesn't matter in a view function. So, and that's one thing that's missing here is like there should be view in there. It doesn't fit on the slides, and that's why it's not there. So, yes. As a quick example of like how you can like abuse the init, this is a very like convoluted example, or very like, I don't know, like quick example. But basically you have your constructor, and in the last thing you just put this like block of assembly, and you're basically returning the actual data you want instead of the code that would be deployed, which is what a init transaction usually does. So you can imagine the way you do this is you build your bytecode as if you were deploying a transaction, include no to address, and then you call the transaction as if it's deployment. And so, yes, please feel free to come up to me afterwards and ask for more information on anything in this talk. But I'm excited about this. There's really cool things we can do with this. Anything that's a view-ish that you don't need deployed contracts for is wonderful. So this is something I feel like everyone really needs to understand because it's so useful. Like people always open issues saying such and such isn't working, and they're like, I don't know why, and they don't give you any meaningful information that you can like work with. So Ethers has an event called debug, and if you do like provider.onDebug, it spits out a ton of data, way too much. You definitely want like a filter, but if you're doing CCIP read, it's a great way to kind of like debug what is going on with CCIP read, because it's a very complicated like back and forth all over the place. So it's nice to see, oh, the URLs are coming back as not an array, or the URLs are including something they're not supposed to, or if there's a failure, like it tells you kind of like where in the CCIP stack things went awry, so you can fix your contract and continue on. Same thing for JSON RPC. There's a lot of times where JSON RPC just returns wrong data, and it's kind of nice to be able to see why and what data you're getting back from the server. You can also just do normal accounting. A huge example, usually when I give this piece of information, because people will say, sorry, I'm talking so fast. So a lot of times people will say like, you know, I'm sending a bajillion requests to the network, I don't know why. They put this on, and then they see that there's a bunch of ETH chain IDs being sent to the network. So then they realize, oh, I need to put like a static network true in the JSON RPC provider. And then they literally just cut all their requests in half. By looking at the debug for like 30 seconds, they see what's going on. And again, like any other analytics you desire, like you can really just examine what's going on. So this is probably the big chunk of the talk I want to cover, which is fetch hooking. So Ethers has its own like fetch library called fetch request. And it's designed to be very flexible because there's a lot of weird things we can do in Ethereum, but it's designed to be hooked a lot. And so the most common hook that I recommend for a lot of people is this, wherever it went, maybe it's on the next slide. It's called get URL func. And so you can give it an alternate method of getting URL contents. So for example, now the defaults are in browser, it uses fetch. In Node.js, it uses the HTTP and HTTPS lib. I mean, it'll be moving to the fetch in the near future. But you can do things like, if you have a data URL, there's no distinction to the library, whether you're fetching a data URL or whether you're fetching a like HTTPS URL or whatever it is. So this is useful. For example, a lot of NFTs have like a URL like a property in the contract. So if you pass the result of that back into this, it doesn't matter whether they're using data URLs or whether they're using IPFS, it'll just kind of get forwarded and you get back whatever the information you wanted. You can also make your own weird, if you really want to do an obscure scheme, you want like weird : / does something, you can use this and you get an opportunity to kind of like intercept that, and now you can implement weird : / to do whatever you want it to do. It's probably useful for like doing Android apps or like universal deep linking and things like that. It's just there for people who want to do weird stuff. So for example, like there's alternatives to IPFS that I don't know about, I don't currently support. For 3 lines of JavaScript, you can now add support for AracNet or Skynet. Skynet, that's the one, yes. Also, so this is a great use of it, is hijacking for transparency. Now this is a very toy example, but basically this is hijacking the get URL func so that every time a request is made to the internet, a pop-up shows up to the user saying, are you sure you want to allow inferior.io/blah to execute? And if they hit no, then the whole thing is just killed. And you could imagine, for example, having a checkbox in your thing saying, you know, don't warn about this domain again, in which case inferior keeps working. Why this is super important, and I think we need more people to start adopting these types of protections. For the CCIP allows reading a contract to send you to some who knows what URL where they can like attach your address to your IP address, like your Ethereum address to your IP address and that sort of thing. And so you can also imagine like intentionally blocking it. If your app is not meant to show NFTs and someone's kind of using CCIP read to like mine this data, you don't even need to present this to the user. You can just like stop it right then and there and say this contract is like malicious or malicious adjacent. And so please go into set, like, you know, whatever you want to, however you want to like process that sort of problem. And you can either set it globally so that you catch everything from any fetch request across all the Ethers library or anything that uses the fetch result, or you can just attach it to like one specific provider if that provider is something you want to like kind of gatekeep because maybe you're connecting to a chain you don't trust or that sort of thing. Yes. And for security, again, I have a lot of like hijacking things because the hijacking is so useful and I really feel like there's so many cool things we can do with it. So, I mean, I don't have an actual example of how to connect to Tor up here, but you could imagine, like, every time you try sending a request to the web, it, like, gets a chance to get wrapped up in Tor, onioned out, and, like, comes back. So if you wanted to like build a more private in like MetaMask, if your MetaMask is using this library, you can just send everything through Tor, whether it's a JSON RPC request or whether it's a CCIP or whether it's looking up an avatar. If you use ENS to look up an avatar, that returns a URL, which points to a URL, which points to another thing. It gives you a chance to kind of like intercept all those steps, forward it to the person you want it to forward to, or funnel it through a SOCKS 5 proxy, or all those good things. Sorry, 1 second. And for example, if you have like bearer, like JWT, you could have one like this bottom example. Every time a URL goes out, the last step you do before it hits the network is it gets signed. You put your signature in there. And the nice thing about this get URL func is it gets called whether it's like the fetch result will automatically handle things like 301 redirects for you, or if there's a 429 throttle, it'll retry. And so on every single request to the network, you get this chance to like inject that like extra data you want. You can like keep the nonce going, that sort of thing. I think there's one more example, which is mockery. Yes. So I use this a lot in Ethers myself for the tests, but you can basically make a URL func that lies to the provider. So in this case, you can see like you build a JSON RPC provider, and it's always going to return block 42 when you call get block number, because it kind of gets that chance to bypass the entire network thing and just gives you back that. So for example, the fallback provider, for those that are familiar, or for those that aren't familiar, it's a very complicated thing that has it nests requests. Okay, let me stack back for a second. It connects to multiple backends simultaneously, randomly issuing a given request to a subset of those backends to look for coordination. So for example, if you want to call ENS and get the address for ricmu.eth, it'll call Infer and Alchemy. If they come back with the same answer, then you get that answer. If they differ, it's going to like knock off maybe Anchor, and it's going to try finding like a coordination between the backends that agrees. So in the event that Anchor was hacked, or in the event that Infura is down, you get like a cohesive result at the end that's kind of been vetted by a quorum of backends. So, as you imagine testing this, it's very hard to test like, well, what happens if Alchemy returns bad data and Infura returns like correct data, but this other thing does really weird gibberish, or there's bad characters in the output. This makes it very easy to test what happens to a provider in these type of situations. You can use it for your own stuff as well. For those that are familiar with knock, it lets you do a lot of things that you can do with knock. Yes. So almost done. I'm trying to leave extra time as well for questions. But so this is just a very short thing. I feel like a lot of people don't realize the power of Etherscan. Etherscan has like verified contracts. We all know that. It's awesome. We all love that like effort we go through to verify a contract. Well, it's nice that once it's verified, you can just provider.getContract, give it the contract address, it'll fetch your ABI, and it will automatically connect you to that contract, and you're good to go. After this, you could imagine doing like c.connect to a signer if you wanted to get like write access to it. But yes, I think we're getting close, if not the end. Yes, haha. And so that is my quick talk on some of the hidden things I feel like are missing in a lot of, not even missing, a lot of things I feel like I want to see more people use. So, yes.
Thank you. Thank you, Richard.
That was much shorter than I expected, but
it's
I
fine.
also finished at 8 a.m. this morning, so.
It's all right. Don't worry. Look, I don't think I did a proper job at introducing you.
Oh, sorry.
No, that's fine. So tell us, what is it you're doing?
So, I mean, I work on a few projects. So Ethers.js, obviously, is like my passion that I've been working on for ages. Oh, nice.
How many people work on Ethers.js?
Just me.
Oh, wow.
Just myself, yeah. I'm trying to recruit other help, but I'm also a little bit of a, like, I'm not a manager. I don't know how to delegate, and so it's hard to, that sort of thing. But the other
This is your baby.
This is my baby, yes, exactly. So, and the other project I'm working on is Firefly. For those that still haven't got one, come find me today. It's like a hardware wallet, it's open source, and all that sort of thing. So
very cool. All right, you have a QR code here. Smash that question button, and we'll get started. Okay, let me refresh. Top question. Wait, I'm not on the right session. Okay, When if simulate V1 support?
So I'm not even familiar with what that is. If somebody wants to like open an issue and post like a link to either like an EIP or like is it a Geth thing or?
Hey, you know what? Let's go to the next question.
Okay.
Can you elaborate on using static network true?
Okay, excellent. That one I can definitely elaborate on. So basically, when you connect to a network, so if you're using, for example, MetaMask, the network can just spontaneously change. So Ethers has to be ready for the network to spontaneously change. If you get the nonce for mainnet, the last thing you want to do is start preparing a transaction with the mainnet nonce on Sepolia. Things are going to fail in horrible ways. You can imagine much worse things happening, like sending things to the wrong DAI address, for example. So Ethers always like checks. But if you're connected to Infera, it's never changing, right? There's never a point in time where like mainnet.infera.io will return to you Sepolia data outside of like catastrophic events. And so you can basically specify in the options that the network is static and that you should not even bother trying to check for it again. Once you get it, just use what you have.
Perfect, thank you. Okay, I have the thing up. And now we can go to the next one. Can the Etherscan contract retrieval also retrieve from other contract repository, like Sourcify?
So it cannot now, but there's no reason it couldn't. If somebody points me to more data about Sourcify, like where the repository is, my guess is they don't run a back end, so you might need to specify the contract address and a provider to connect to. But I mean, that's like 5 lines of code. So I mean, I'm just not familiar with a lot of these other services. There's just so much in the space to keep up with. So for sure, open an issue on GitHub or come talk with me afterwards. If you're a Sourcify person trying to push your Sourcify thing, I fully endorse that, and I want you to come like bug me to get added as well. Yes.
That makes sense. The next question is cut in half, so we're going to skip it. Can you tell us how Ethers is better than Vim?
So I feel like this is I kind of expected a question along these lines. I'm a big fan in general of like diversity. So it's not about necessarily better. I feel it's very different. The big difference I see is VM is very much designed around functions, which is great for tree shaking, but I feel it makes things more difficult for developers. Ethers is very like object-based. You can't tree shake a class in a meaningful way, so that's kind of like you can only tree shake at the kind of the file or like the object level. At the end of the day, I don't really worry too much with that. Like the thing is, I wrote Ethers for me, so it's what I use. It's kind of using the paradigms I care about. So I don't really have a lot to say about that. 'Cause I mean, I have not used VM other than like looking at it. I've talked to the guys. Like it is. Yeah, I've got nothing more to really to say about that. Unless there's something specific. Feel free to be specific.
Nice. So one of the challenges for developers is to get historical balances of ETH and L2 chains. What do you think could be the best way in the future to get these without an archival node in place?
I mean, I can totally imagine a place where there's something like the graph, but for like historical data. We really need some sort of service probably to support that. And like the economic incentives around providing that data always mean that you're basically going to need like some sort of paid service like an Infera or whatever. Unless, I mean, if anybody has brilliant ideas, go for it. If there's a service that Ethers can use for that, please, like tell me, again, I feel like the moral of the story is tell me about it because I want to add these things if they exist. But it's definitely not something, it's not a service that I could write or host. Like this is just petabytes of data that would be, well, it'd be gigabytes of data with petabytes of indexing into that data. So
it doesn't seem like the kind of stuff you can ship in Ethers, but it's a service people should be.
Right, and if it's a service that exists, like tenderly, I will totally provide an Ethers way into it.
Nice, thank you. Can you elaborate on using static network?
Oh, is this more than the last one?
Yeah, this one is the one that was voted.
Okay.
If you want to pick another one, go ahead. Which one do you like more?
Oh, I mean, I thought I answered that one.
Oh.
Okay.
Sorry, I didn't mark it as...
Sorry.
Okay. Is there a way to implement custom RPC calls? Some chains have non-standard one.
Absolutely. So if you have a JSON RPC provider, you just do .send, you give the ETH method, and then you give it whatever ETH method for that network takes. Oh, for sure. Like, this is the way you should be processing a lot of... oh, there's a thing I should have added to a slide. It's too late. I'll remember for next time. But yes, for sure you can add like custom, like it's required. Like a lot of chains have their own like exotic behaviors that are really useful to be able to like access.
Okay, we'll get you where you were a bit early, so I'm gonna take another one.
I was gonna say I have 41 seconds left on there, but yes.
It's okay. So you showed something about making requests over Tor. Why is it useful to make requests over Tor when you can't really run an Ethereum node over Tor?
I mean, these serve different purposes, right? Like, if your avatar is being served on the internet off of some web server, you might want to protect your IP address from being attached to that necessary avatar. I mean, I understand the sentiment of the question. It would be awesome if we could Torify like Ethereum, but there's still lots of like privacy value in talking over Tor. That's also like a toy example. You could imagine other weird transports where you're basically trying to send data over like a BLE network over. Maybe you're inside a really busy venue like this, and you can imagine having like a BLE Firecast style communications protocol. So you could implement that on top of that if you wished. But I mean, I'm still a big fan of Tor. I think Tor needs, I don't know whether funding is the right word, they need something, but Tor is awesome. And so there's lots of privacy-focused things where Tor could be useful still.
Richard, thank you for your talk. Thank you for your work. Frog Bump.
Thank you, thank you. Oh, Frog Bump, haha. I love it. Cool, thanks.
And to everyone, we're going to start the next session in 5 minutes. Stick around, it's going to be awesome. Hello, can you hear me? Nice. Okay, get ready for our next talk. Our next speaker is Anthony. He leads applied research at the Nomic Foundation. He's going to talk to us about Slang's query API. And I guess he'll explain what Slang is better than I will. Don't forget, during the session, you'll have a QR code here. And ask questions, upvotes the one you want to see answered, and then we'll cover them at the end of the talk. All right, please welcome Anthony.
Okay. G'day. My name is Tony. I work at the Nomic Foundation in applied research. I was previously a co-lead on the Slang project, and it's in this capacity that I'm going to speak to you today. I have a fantastic job working with excellent people at Nomic. Nomic is a non-profit, and our number one core value is kindness, and we live this every day. And we are hiring. There's meant to be a QR code at the end of my slides, but I'm afraid it didn't make it. And I want to give heartfelt thanks to the co-founders of Nomic, Pato and Fran, for creating and maintaining such an amazing place to work. So, today we're going to explore the Slang Query API, which is a new feature which makes working with Solidity code surprisingly straightforward. And now this is not a tutorial, so some of the details have been omitted. You can't copy and paste any of the code that I'm going to be providing. It's just so that you can, well, I'm hoping to inspire you so that you go and find out some more details. Okay, so 20 minutes is a bit of a sprint, so I'm going to speed up. Let's go. Okay, so what is Slang? So Slang's our Solidity compiler library. It's basically a developer tool that enables you to write better tools. It parses and analyses Solidity code from version 0.4.11 to the latest 0.8, which is basically all of the Solidity code that is live. Our focus is on correctness and convenience. We're about to release version 1, which covers the typical front-end features of a compiler. And our main objective, as I said, is to enable you to develop better tools. Slang has a radical, open, declarative meta-architecture. Slang's an error-correcting compiler, so it always produces output, even if you've got source code errors. A key feature of Slang, which is what we're here to talk about, is its query API for code analysis. So compiler front ends fall into two main categories. There are those that produce what's called concrete syntax trees and then produce an abstract syntax tree from that. And there are those that produce abstract syntax trees directly. So what's the difference between concrete syntax and abstract syntax? Well, concrete syntax, as you can see on this slide, is a complete representation of the source code. It includes every character, every bit of white space, every comment. It's like having, as I say, like having the full book, like a PDF. Whereas an abstract syntax tree is a simplified tree representation. So it doesn't include white space and equal signs and punctuation. It's just got the essential details. It's like if you were reading the plot of a book, but you didn't actually have the text. So here's an example of a concrete syntax tree. So we've got a simple variable declaration here, and every single element of the original source is represented. Nothing is removed or simplified. Now, this is different from an AST, which will eliminate some of these details. So if we look what we've got here, it's a simple variable declaration. Now it consists of a type name, which is uint, and then some white space, an identifier, some white space, punctuation, the equal sign, some white space, a number literal, 1, and then the semicolon. Now, what's crucial to understand is that we're preserving every single character. In fact, even if there's an error in the source code, you'll find it in the concrete syntax tree. So why is this important? Well, when we're developing, building developer tools or transforming code, we often need the complete information so we can round trip. If we were just concerned with the meaning of the code, then we'd use an abstract syntax tree. But for many tools, like formatters, linters, or refactoring tools, we often want the full syntactic details. You don't want to lose comments when you're refactoring. And sometimes you want to know if you've left 2 blank lines, and you want to preserve that. This level of detail is great, but it's also challenging. It's quite difficult to process this. On the one hand, we have complete information, but working with detailed trees can be complex, and that's the challenge that the Query API solves. So from now on, I'll omit trivia nodes and white space from the examples. They're still there, but I don't need to show them. So let's look at a slightly more complex example. This definition shows how different elements nest within each other. And once again, notice how everything is preserved here. We've got a function definition, we've got the keyword function, the identifier, we've got a parameter list, which in this case is empty, but we still preserve it. And then nested in that is a block and a return statement, and so on. Now, this level of detail allows us to maintain complete source fidelity. As I said, if we're going to round trip, we can track precise code locations. So if you want to do error reporting, it handles formatting preservation. And when you're building development tools, this detailed structure is essential for a certain class of development tools. So to emphasise this point, and I know I'm being repetitive here, I really want to make this point though, why do we need a concrete syntax tree? Well, we really want to, in a lot of tools, for example in Prettier, which is now using Slang, by the way, using this technology, Prettier Solidity, we want to make sure that we can preserve every single character, especially comments. For example, you might have a tool that wants to deal with comments, wants to encode validation information in a special comment format. Not like the documentation comment, but your own special comment format. So you want to preserve those comments. An AST, on the other hand, is focusing on the essential structure, which is good for semantic processing, doesn't contain the formatting information, simplifies expressions, and it omits all comments and white space. So now that we understand what a CST is for, let's look at how you might traditionally process a CST. So this is the kind of code that you often see a lot of. You know what it's like to traverse a tree, especially a very deep and complex tree, which is what you typically get out of a compiler. And it's not pretty. What we're trying to do is actually quite simple. We just want to find all the variable declarations in some Solidity code. But look at what we have to do. So first of all, we're writing a recursive function. We need recursion because we don't know how deep in the tree it is. Could be at the contract, inside a function, inside a block, anywhere. And then when we find each node, we've got to manually check its kind, we've got to search through the children, we've got to handle all the edge cases, and we've got to manage the recursion stack, especially if you're threading state. And this is a simple example. In real-life code, you'd have to handle error cases, deal with unexpected node types, which is what you can get if you've got a source code error, for example. Manage your state during traversal, and if you've written a visitor pattern, you know that it's a pain in the ass to manage your state. You've got to handle parent references, and you've got to manage the position in the source code. Now, the problems with this approach are numerous. First, it's incredibly verbose. The amount of code you need to write to do even simple analysis is substantial, and the more code you write, the more you have to maintain, and the more places there are for bugs to hide. Second, it's error prone, not only because of the volume of the code, but also it's quite tricky to write these when you're dealing with complicated trees. For example, in Solidity, variable declarations can appear in for loop initializers. I don't know if this code would handle that. It's a question for the reader. It's hard to maintain. When the language evolves, and as you know, Solidity evolves significantly in all sorts of interesting ways, like in one of the 0.5s where the exponentiation operator changed its associativity. So when the language evolves, you need to update your traversal code. And that's because the traversal code is mixed with the analysis code. So what you want to do for analysis is mixed in with the mechanics of traversal. To make changes, you're often going to break things. Finally, and more importantly, this forces you to think about what or how you want to do things rather than what you want to do. And the intent of this code, finding variable declarations, is buried in here. You could look at a big bit of traversal code and you wouldn't know what it was meant to be doing. We need something better. So we'll have a look at some specific challenges with manual traversal. So recursion management. You've got to handle deep nesting efficiently, avoiding stack overflow. You've got to make sure you don't have any infinite loops. You've got to maintain your context, state management, and you've got to know when to stop recursing. Once again, if you use a visitor pattern where you've got an external visitor external code driving your visitor, you often want to stop, or you don't want to go into the children of this node. How do you do that? That means you end up with a more complicated API. State tracking is quite complex. You need to keep track of the parent node. When you're walking a tree, you need to maintain scope information in the case of a compiler, build up your composite results, handle cross-node relationships, i.e. you want to link this node which you visited 30 minutes ago with this other node which you're visiting now. Now, error handling just multiplies the complexity. And edge cases keep appearing. For example, parenthesised expressions, nested structures, optional elements, and language-specific quirks, of which there are plenty in Solidity. And finally, you've got a big maintenance budget. Now, I know I'm repeating this point, but this is significant, as you'll see when we get to queries, which I think is the next slide. So this is where queries come in. So let's look at how we solve some of those same problems using queries. So this is our first example. We want to find all the uint variable declarations. It's as simple as saying in variable declarations where the type name is uint and it's got an identifier, bind that and return it. No traversal. No edge cases. Hardly any maintenance. No efficiency problems. So the second example shows something a bit more powerful. In this case, we want to find immediately nested function declarations, i.e. a function inside another function. So here we're saying in every contract definition, there are some contract members. In the contract members is a contract member. For every function definition in there, find the block and look for a statement in there that is itself a function definition. Bind that to a variable called nested and return it. So why is this so powerful? Well, first of all, it's declarative. We're saying what we want, not how we want to do it. Makes our code easier to understand and maintain. And when you look at this 2 months later, it's obvious what it's doing. Whereas I'd suggest that you'd have a couple of pages of code traversing your tree if you were using manual traversal, and it wouldn't be obvious what it was actually meant to do. So it's structure aware. So the query understands Solidity's syntax structure. It knows about scope and it knows about nesting. And it also knows where type name, for example, in the first case here, appears in the tree. These patterns are composable. So we can build complex pattern matching from simple pattern matching. So if we wanted to find uint variables within these nested function definitions, it'd be as simple as putting that, appending that first query below the second query. But most importantly, this is focusing once again on what we're trying to achieve. We can think about code patterns and structure design without getting bogged down in the implementation details. So let's have a look at some more advanced query patterns. This one isn't that advanced, but for example, in an unchecked block, you want to find all function calls. It's easy as that, and it's obvious what it does. You could write this on one line. The second example is a bit more complicated, but here we're looking for variable declarations, state variable declarations that have a type that is either a mapping or an array. And think about what this would take if you were doing manual traversal. You'd need scope tracking, type checking logic, complex conditional logic, and you'd need to carefully handle the nested structure here. So what are the use cases for this? Well, some use cases, because I'm hoping that people come up with far more use cases than we know. We want sort of emergent benefits from this. Well, if you wanted to have custom coding standards, you want to enforce custom coding standards, you've got project-specific restrictions that you want to check, or you want to do version compatibility checks, so you want to make sure that you don't use certain features of Solidity. Style checking, well, if you've got specific naming patterns you want to enforce, specific structural conventions, and you can have context-aware rules. Now, you might be thinking, well, can't I use a linter to do this? Well, yes, but this is meant to write the linter. This is designed for writing linters, so that's why these are the use cases. This is not an end-user tool. This is a tool for developers to write tools. So you can do pattern detection, anti-patterns, for example, optimization opportunities, which may not be immediately obvious if you've got a big library of things, detecting complex structural patterns that you might want to simplify or mark. So once again, this is a kind of an ESLinter equivalent. Code transformation, automated refactoring. Refactoring is transformations that preserve the semantics. Code modernisation, it's very easy to write patterns that then transform into more modern code. Automated modifications, i.e. things that aren't refactorings, that actually change the code. And formatting. And as I said, Prettier Solidity is already using Slang. One important point I want to make here is that we support WASM, and we support specifically the component spec and WIT. So for those who know what that means, this means that all of this technology works in the browser. It's also available as a Rust API or as TypeScript, which is our first target because most people are using TypeScript. So some more applications, code transfer, I've already done that. Documentation generation, it's easy to generate automatic documents by extracting function signatures, doing structure analysis, checking for particular usage patterns and documenting them, and processing comments. As I mentioned before, you might have validation information in a certain specialised comment format. Now, you can also use this technology in combination with AI tooling, for example, to produce diagrams from your code. You can use this by encoding the Slang API as a RAG. So what are the key benefits? Well, structure-aware queries. Your queries naturally align with the structure of the code that you're trying to match. You don't have to think about trees and nodes and traversal. Complete syntax preservation. You never lose information. You can perform transformations without losing the formatting, and you can round trip from a CST back to source. Efficient pattern matching. So we can spend all the effort required to make this efficient. If you know anything about the state of the art in terms of tree pattern matching, and in fact we're not a search engine, we are a unifier. So we use a prolog/datalog based mechanism which returns you all the potential matching results, not just the first one. You can avoid unnecessary traversals, we can cache results, we can index the syntax tree, make it very efficient. It'd take a lot of effort to get the same result if you were doing it yourself. Composable syntax rules. You can combine simple rules to make bigger ones. You can have a big library of these patterns and you can reuse them over your code. Share queries between your projects. You've got maintainable analysis code. So the queries express your intent, not what you want to do, how you want to do it, but what you want to do. Your code is shorter, it's easier to understand. Any changes to the language, we take care of that. Slang takes care of that, so you don't have to. Less code means fewer bugs. And these benefits compound. It's not 1 + 1 + 1. It's, the whole is far greater than the sum of the parts. So what impact does this have on your development? Well, before using this query API, you'd spend significant time writing and debugging the traversal code, you'd struggle with maintaining the analysis logic, and you'd face challenges when adding new features. After it, you end up with clear focused code, it's easy to maintain, you've got a robust implementation, and it's highly extensible. And that is it. Any questions?
Fantastic. Thank you, Anthony. All right, let's get with the questions. So, folks, remember, you can scan that QR code, add questions to that list, smash that upvote button so that the most interesting question gets asked. Let's go with the first one. What are advantages to using Slang compared to SemGrep?
Well, I must admit I'm not familiar with SemGrep, but I know the general concept. The specific thing here that this is a programmatic tool that you use to build other tools. Now, of course, you can combine things like SemGrep, I imagine, but I don't know if that is something that you would include in a tool for analysing lots of different versions of Solidity.
That makes sense, thank you. How does Slang differ from a fine-tuned LLM? Could Slang's modularity allow to use LLMs in the future?
Oh, I'm in applied research, and this is something that is very actively under research. I'm not making any commitment, but if you've used fine-tuned LLMs, and I've used them a lot, for example, a lot of the code that I write is actually written by Claude. A lot of this presentation was written by Claude. Amazing tool, but you always need a human in the loop. So yes, you can do this using LLMs, but the thing with LLMs is that they are a human augmentation tool, whereas the approach that we're talking about here is exact and precise. If you've used LLMs to do this, you know that you spend a lot of time on prompt engineering, and then you cross your fingers, and something comes back, and it doesn't quite work, and you prompt it again, and so on and so forth. So yes, this is certainly something that could be included in the future.
There's a chance, but maybe not now. I mean, not immediately.
Certainly not now.
Okay. Are the limitations of a tree-visitor-based approach not solved by using an API with CFG and intermediate representation like Slither provides?
Well, if by CFG, well, you're either meaning two things. You're either meaning the control flow graph, which is typically something you'd find in an abstract syntax tree, or if you mean control flow as exposed by Rust, for example, and this is something where you reify your control flow. So you return a token in your visitor which says, do you want to continue? Do you want to go down the trees? Now, this tree visitor, these Slither may well solve the same kind of problem. We have a different set of constraints. For example, our query language is intended to be extended with semantic predicates and with the ability to do arbitrary recursion by skipping over arbitrary subtrees. So there's a lot that we want to do there. So I wouldn't say that in Slither you can or cannot do that. I'm not familiar enough with Slither.
Perfect, thank you. Is there a question you like most in there?
Well, with this work with different EVM versions, yes, it will, because we're dealing with source. We're well before EVM. Slang is a compiler, and it'll produce bytecode. So that's a question about the compiler, not about querying. Have we published the grammar for Slang? Yes, we have. Slang is actually a declarative meta project, so you can use it for any programming language, not just Solidity. And we have published that. Everything we do is open source. Nomic Foundation on GitHub, all of our development is in the open. You can reuse all of this.
Awesome.
How important? Well,
how important is it to maintain code with different Solidity versions? Why not just use one version?
Because if you want to be able to provide tools that analyse a large number of contracts, which may be an earlier version of Solidity than the latest one. For example, 0411. There's a contract on mainnet that is 0411. You want to get the source to that. You want to provide analysis tools for it. That's why we want to support all of these versions. Now, we don't go back to 001 or whatever the first version was. So we're pragmatic about it, but these are the versions that are live. And our goal is to support all the versions that are live.
How do you determine the cutoff version? What's pragmatic?
Analysis of mainnet and all the contracts that are live.
Okay, is it the number of contracts? Is it the value stored in those? Is it the amount of transactions going
No,
through those?
the earliest. I didn't do this analysis, so I must admit I don't know what process we used to determine that, but it is the case that the earliest contract in use, apparently, is 0411.
Fantastic, thank you. What's the best practice for using Slang to analyze a large number of programs? Where should the data be stored and in what format? Imagine this is something you run locally, correct?
Yes, it is.
Perfect, thank you. All right, what update in Solidity was the hardest to adapt for? You mentioned quirks and weird updates in Solidity. Which one was the hardest? Or
none of them was particularly hard. The volume of quirks is what is a challenge. I mean, we've got hundreds of edge cases. We had to analyse Sol C because that's the only definition of the language. And go through the code and then test it and then go to Sanctuary and look at massive numbers of contracts, run our compiler over them or run our parser over them, what breaks, what doesn't. We've got extensive test cases. So that was the challenge. It's the number, not any particular difficulty.
Fantastic, thank you. Do you dream in bytecode?
No, I don't dream. I dream compilers, actually.
Nice. All right, Anthony, thank you a lot for your time and all the best to you.
Thank you.
People, our next session will start in a few minutes. I am off for today. Thank you for those who spent a bit of time with me this morning. And I'll see you soon. Cheers.
p.m. I hope everybody's enjoying their time. My name is Robert, a developer advocate at the Starknet Foundation, and I'm going to be your MC for the rest of the day. Now, I would like to introduce the next speaker, Ernesto Garcia, who is a smart contract engineer at Open Zeppelin Contracts, and he will be discussing about how to bring your own cryptographic identity to smart accounts. Please give him a round of applause.
How's it going? Okay, is it working? Perfect. How's it going? You're doing great? Perfect. Okay, so what we're going to do today is talk a little bit about smart accounts in the context of Open Zeppelin contracts. This has been a really requested feature that we had been working on for quite a while, and we have a couple of things to discuss on regarding this. So let's get into it. All right, so this is the agenda. First, we're going to start with a little bit of background. Where are we starting from this work? Also, how to do account abstraction, like on a general perspective, just as a quick recap of what account abstraction means. Then we're going to custom signature algorithms, which is one of the main topics and is the thing that is like the most important about this talk. We're going to go over some technical goals we have for an account implementation in Open Zeppelin contracts. Then we'll review a couple of security considerations we have to understand to make better accounts. And finally, I will guide you through a quick way of how to build an account using Open Zeppelin contracts. I'll let you know, but like all of this code is already on alpha, so we will be releasing over the following weeks. Okay, let's start with some background. The first thing you need to know is that we recently received a grant from the Ethereum Foundation to work on account abstraction, right? So this means that we are going to make a library that is consumable for you developers, so you can use Open Zeppelin contracts the same way you have been doing it before. And in this way, you will have available like a couple of variants for making accounts, extending accounts, and also having some primitives that you can use on your own accounts if you want, right? Given this context, we started doing some research, and what we found out is that there is, number one, already a wide range of implementations, right? Like we already know a couple of implementations out there, some quite popular like Alchemy, Safe, Biconomy, and some others, right? So basically, like all of these development that has already been made, like we don't want to compete with that, but we would like to provide a way to also like create new accounts, innovate on top of these ones, and also providing primitives to also enable developers to build on top of those. Second thing is that there are a couple of emerging security challenges that have come up because of the explosion of creation of accounts. So we want to address those as well and having a clear framework for you to move forward when you're building an account. The next thing is that there is a lack of a straightforward approach when you are trying to build your own account. You basically have to research a lot of different implementations if each one has different modules or approaches to bring your own functionality. So the idea is that you should be able to have more expressivity on the way to design on an account, and also you should have like a straightforward path, right? Like the same way you use import ERC20 and literally you use deploy it, there should be something similar to that, right? So, okay, our observations of this sort of research is that we would like to divide or layer the account implementation into like different layers. The first one should be like a base layer for ERC4337. The thing with ERC4337 is that it only defines like a very simple and what do you call it, like, yeah, simple interface, right, and a set of rules. But on the implementation, things can get very different. So we would like to have like a base layer for ERC4337 account that is super solid, battle tested as everything in Open Zeppelin contracts is. Then from there, we go to the validation layer, which means this is like the place where you put the logic to validate a transaction, right? If you are using a regular EOA to sign a transaction and putting it into an account, this is where the logic for validating the signature should go. We think this thin layer should be also kind of customizable, and you guys should be able to bring your own functionality at this layer, right? Although there is another layer, which is the modularity layer right here, in which there are a couple of competing EIPs or standards. We think there is a lot of innovation coming on here and also happening right now here. So yeah, we want to provide you like a way of using either a custom validation mechanism on the previous layer and also like a modularity approach if you want to. Finally, the idea is that we have, or we end up having a similar to a wizard-like experience. Who has used wizard, like OpenZeppelin wizard from here? All right, so for those who don't have context, OpenZeppelin wizard is like our tool to build smart contracts in an opinionated way. So you can go to wizard.openzeppelin.com and you will see what I'm talking about. So basically, we would like you to come to Wizard, create your own account, just select a couple of options, and you're ready to go. All right. Talking about mass adoption, I think we have been very hyped about the fact that account abstraction is bringing a lot of opportunities to bring new people. But there are a couple of challenges we need to address first. So we'll eventually get there, but there are a couple things to do. In order to understand what we need to do, there are a couple of related ERCs and best practices you need to understand and follow. The first one, of course, is ERC 4337. I mean, is the base ERC. And it has a couple of rules that are quite interesting. You know, all that is related to paymasters, aggregators, all of that is quite complex. We'll eventually get there too. But for now, we want to focus on the account side of 4337. Then the second ERC to take into consideration is ERC 7562, which corresponds to the validation, storage validation. Well, not storage. There are a couple of validation rules for 4337, but the main or the most important ones, in my opinion, are the storage validation rules. Why is this important? Because there are some, what you call it, like setups in which you can create an account, and basically you are violating some storage rules, some storage validation rules. Why is this important? Because otherwise you wouldn't be able to use the decentralized peer-to-peer network to process user operations. You can still use a private bundler, that would be fine, but ideally we would like to have an implementation that works out of the box with the decentralized network. And finally, ERC 7739, this is a thing we stumbled upon when we were implementing the account. Because basically, there are a couple of issues with replayability if two accounts are owned by the same key. I'll get into that. But this is a cool ERC to get to know more about like how to bind a signature to a specific account implementation, which is pretty important to avoid replayability. All right, so let's get into how to do account abstraction, just for a quick reminder. Remember that a smart account is way more than just the validation mechanism, right? You can add modules, you can have like custom logic, all of that. But ideally, you will focus only on the validation logic if you are building your own account from scratch. From this, we have seen a couple of amazing innovations like ZK email, which is using your email to send a transaction from a smart account. This is pretty clever. Also, ZK identity, we have seen a couple of options like using passports and these kind of things. So this is why we think the validation logic layer is like an important part that should be extensible for developers, because a lot of innovation is happening right here, but it's being brought up as modules, which is also a valid approach. All right, so ideally this is what you should do if you're using OpenZeppelin contracts. This is not public yet, we're still working on that, but this is like what we are trying to achieve. As you can see, it's only importing an account ECDSA. In this case, this is controlled by an EOA. And there are a couple of things to note here. Let's get into that. So number one, is this upgradable? Not really. The thing is that in order to create an account, you probably will need a factory, right? And if you need a factory, you basically need some way of initializing the account. So upgradable contracts are perfect for initializing, right? They are basically designed for that. And it doesn't mean that the account is upgradable. It just means that it's a clone that you deployed and then you initialized. Second thing is, it is a draft. Well, yes, some of these ERCs are still a draft, so we have a couple of challenges there because we guarantee backwards compatibility for all of you, so you don't have to manage or deal with that. So based on this, we wanted to, or we want to provide you with an implementation, but make it clear that it is still a draft. A couple of things may change. And of course, we will keep working on this, and we appreciate the feedback. Next thing is it clonable? Yes, because as I mentioned, you need a factory, and because of this, you basically need some way of cloning an account so that it is pretty cheap to just create and generate new instances of accounts, right? Okay, so let's get into custom identities or custom signature algorithms, which is the main thing we want to discuss here. So to get into this, let's explore a little bit on digital signatures, right? Right now, the majority of implementations of account already use some sort of validation mechanism, or they accept something like ERC 1271, which is for smart contract signature validation. So in this case, then the most naive approach to bring your own cryptographic identity to a smart account is just use an interface like 1271, include the validation algorithm, and then you're ready to go. But in reality, digital signatures are more than that, and we have seen that, for example, a couple of traditional public key infrastructures, like in governments, corporations, banks, and these kind of environments, these are already widely used. It's just that it's not used in the context of a smart account. So this is why it is important to bring your own cryptographic primitive, because it makes it easier for players in the industry, let's say traditional finance, to just come here, use the same key they were probably using for authorizing transactions within their organization, and they should be ready to go. So they are widely adopted as well. And battle tested, I'm adding a quote here because, well, it's not the same environment. They have been around for years, but like in closed environments, it's different to these, to the crypto industry where everything is open source, is pre-battle tested. So yeah, I think this is a cool, it's a cool experiment, but definitely we need to see how it behaves over time. All right. Particularly with this thing, the wide adoption of some digital signature schemes regularly means that it's cool for regulation, right? There is some sort of regulation around like traditional finance using access control mechanisms, so we can also leverage that for real use cases. Right now, in open sampling contracts for signatures, we already have 3 different signature algorithms available. The first one is the good old ECDSA, right? The one that is controlled by an EOA. This is already there and has been there for a couple of years. We recently implemented a P256 implementation. This is in Solidity. And the reason why we did it is because we identified that some chains, particularly some L2s, may not have already enabled RIP 7212, which is the one that validates these kind of signatures. So because of that, we came up with an implementation that we think is efficient enough and is well designed for you to use it. But also, if it detects that the precompile is available, it will fall back to this precompile. So you can use it out of the box, removing all of the considerations that you should have as a developer. You use import it and use it as everything in open sampling contracts. Also, we are adding our RSA library. This is because we have found a couple of government public infrastructures that depend on this particular algorithm. So it is there for consumption. Also, it's pretty popular in some use cases, like, for example, DNSSEC. ENS, probably you have your ENS, but ENS depends on this algorithm for some DNS providers. So it's also a good primitive to have. We already have it in open sampling contracts. All right. Let's recap a little bit on what a digital signature means, just for you to understand a couple of issues that are coming. So basically, a cryptographic signature is just a message that you hash. You generate like some piece of data, bytes 32, and then you use a private key with a signature algorithm to produce a signature, right? Eventually, then you will use a public key and your signature with the same digest to pass it through a verification algorithm, and it will return true or false depending on whether it was successful or not. So the thing with this is that we can find out that there are 2 main algorithms in this. Number 1, there is a hashing algorithm, and number 2, there is a signature algorithm, right? So this is important because you as developers, you probably will be constrained by whatever is an off-chain, is off-chain signer, right? Usually people already have like a device, a YubiKey, some sort of software that doesn't depend on you, and is probably using one of these custom hashing algorithms. We're pretty used to use Keccak 256, But in reality, some signers, like off-chain signers, for example, the one you have on your iPhone, the secure enclave, will try to use SHA-256, right? So this is not really a problem, like we can just rehash it, but we think this is too opinionated, and this is the sort of thing that we would like to have more contribution and opinions from you. This is basically the idea, because some of the off-chain signers are constrained to specific algorithms. Like, we need to work around this, right? And this will happen depending on how you compose your accounts. It's probably becoming a mess if we don't take care of like standardizing this or something similar. So another thing to take into consideration is replayability across same key accounts. This is, let's say you have account A, account B, and both are controlled by the same key. Well, then there is the possibility in which if you sign a transaction to send, let's say, 1 Ether to Vitalik on one account, that same signature can be used on your other account to transfer 1 ETH again to Vitalik, right? This is not ideal. This is an issue that was originally discovered by Curious Apple. There is a good write-up on the internet that you can also search. Just look for replayability on smart accounts. You will find it. So the idea to solve this is that we need some way of binding the signature to the current domain in which it is used, right? So this is perfect to do, EIP 712 is perfect for doing this. Are you familiar with EIP 712? Okay, I see a couple of hands. For those who don't have any context, EIP 712 is a way of constructing signatures with types. Basically, you can sign a message that has an uint256 type and a couple of others. It's like a struct you can sign. And what is special about this struct is that it also includes the address of the current contract and also the chain ID, which makes it, you cannot reply a signature because it is bound to the current implementation that you're signing the message for, right? This is actually what ERC 7739 is proposing. It's like a way of rehashing a hash so that it adds some context for you to understand better what is going on instead of just signing an opaque signature, an opaque hash, sorry. So, all right. Next thing is, another thing to consider is that what if we want accounts to be owned by accounts? So in theory, this is possible. Like, we have seen multi-signatory schemes in which you have a single account owned by multiple accounts. But in this case, if a smart account wants to own another smart account, it comes with a lot of gotchas. The first thing is like, okay, if B is owner of A, what should B sign? Like, should they just sign a message that is for the domain of B? Or should it sign a message for the domain of A? What if there is another domain? Like, probably you're signing from B to authorize on A an interaction with an application C, right? So it's starting to become a mess in this way, and it's becoming opaque for whoever is signing this on their user side, okay? Second issue, like how should we validate from A that the signature is correct from B, right? Because this has to do with storage validation rules in 4337. So yeah, like for example, if in the validation phase, which is literally where you check signatures, if you go to another contract and check storage, let's say to recover the public key, then you are violating some of these rules, right? So these are some of the challenges that come in when you want to like add composability to accounts. We have found this as an issue. And we, of course, want to work like to solve this. Just a quick quote. This is a popular joke in computer science. There are 3, not really 4 things in computer science, and one of these is signatures in account abstraction wallets, right? But yeah, this is why we want your collaboration, and this is how we're doing it. Basically, we have 3 main goals with our implementation. We want it to be secure. We want it to be layered, and we also wanted to make it extensible, right? We don't want you guys to start open sampling contracts and then become vendor locked in to whatever we have. Basically, the idea is that you can take any of the components and use it for your own implementation so that we can foster a better innovation space and also a more expressive, way of creating accounts. For this, there are a couple of security considerations, like, for example, we want some audited building blocks for you to be safe whenever you're building your account. Also, we want to have a strong cryptographic primitives. These have been audited by the research team at Open Zeppelin, so shout out to them. They have been doing an amazing job. Number 3, replayability issues, as I mentioned. Number 4, we would like to maintain user operation readability. We don't want the user to end up signing something they don't understand, because this is super dangerous. And number 5, we want it to be community-driven, which means we really want your feedback on this and try to co-own the development with the community. So this is how we build an account. This is ideally the sort of steps you should follow. So number 1, you pick a base account, starting from account base, which has a virtual function for validation, right? Then you add your 7739 signer, and from this you get immediate replayability protection. Then you just have to fill both virtual functions that are there. One of these is the validate signature using ECDSA recover, and you don't have to worry, this already has the replayability protection in place. So whatever you receive as a hash is already bounded to the account. Number 4, use deploy, and that's it. Thank you so much. Is there any question?
Thank you, thank you. So now we're going to the Q&A section. For those who want to ask any questions, we have this QR code on the left. Scan it, add your question, and upvote questions that are very interesting. Thank you, Ernesto, for the talk. Now we're going to ask, I think we're going to start with the popular questions. So the first one is, why not incorporate all or as many popular algorithms so as to apply to as many external opinions and implementations?
Right, this is a great question. The honest answer is that it is really difficult to implement cryptographic schemes, especially in Solidity. It comes with a couple of challenges, so it's a tiring process, right? We're open to receive contributions on that. It's just that it is exhaustive, it takes time, and we also have to audit those. Also, I forgot, but at the end of the presentation, there was a QR code for the community repository. Everything that you want to add, like on the community side, is welcome on that repository. We have less, we have more relaxed policies on that repository, so everything is welcome from your side.
Fantastic, thank you very much. Now for the next question is, would you be able to implement your own custom functions such as 2FA or social recovery?
Yeah, the short answer is yes. The long answer is that we would like to understand exactly what it means to have 2FA, right? Because what if we want to be compatible with like regular Web 2 workflows, or do we want something completely new that is EIP 712 based, right? These kind of things are like worth discussing, but we eventually will get there.
Fantastic. How can we solve fragmentation problem in ERC 4337?
Good question. I would say having like a sort of, what do you call, like a straightforward framework, like a set of steps that are pretty clear enough to everyone, we'll probably sort of solve it, but in reality, we already have implementations. So I guess we have to work out and, work around them, which is like the usual, what do you call, like is the way things work, right? We just like continue building on top of what is going on.
Gotcha, yeah. Okay, so for the next question, there are a few conflicting EIPs for plugins and modules. Will Open Zeppelin take an opinion on these, or will leave that up to the implementations?
Also, really good question. We would like to have an opinion because we don't, usually we try not to provide you with 2 versions of the same thing, right? But like we definitely need to experiment with these modular standards to understand for which cases are better. So probably our opinion will end up looking something like, okay, for these use cases, you should use this ERC, and for this other, you should use this other. But again, we are implementing this on the community repo of Open Zeppelin contracts. So basically, all of the ERCs that are for modularity are very welcome to be implemented from contributions from you.
Okay, and we have one more question. If you want to ask more, feel free to do it. Is it possible to create smart accounts that work with iPhone security enclave? So I guess with a different signature.
Yes, 100%. The P256 algorithm that we just implemented is the one that is used by the secure enclave. So yeah, you just need to create your account. Make sure that you can select, make sure that you're using the same hashing algorithm as in the enclave. This is just pretty easy. You just grab the message or the hash in another hash, and that's it. But yeah, the answer is yes.
Nice. And I think I have one question from me. What's your favorite thing about account abstraction? What you're trying to solve overall for the general users?
Yeah, I think I'm excited about users bringing, usually users already have some way of authentication that they are familiar with. And I think I'm pretty excited of seeing all of these people bringing this into their own accounts so we can onboard people more easy.
Fantastic. Ernesto, thank you again for the wonderful presentation on smart accounts and account abstraction. Please give him a round of applause. Thank you very much. Okay, and now I guess some of you are a little bit hungry, so we're going to take a lunch break. You can go grab some food. The break is going to be roughly about 70 minutes, so we're going to be back at 2:40 p.m. With the next session, the evolution of ZK. See you in 70 minutes.
Hello, hello everyone. Hope you had a fantastic Devcon. Hope you had a nice lunch break as well. We're very happy to have this kind of like last-minute submission. Also to have this announcement coming from Josh Davis and Nixo from protocol support at the Ethereum Foundation. And so with no further ado, we'll welcome Josh and Nixo to jump on stage. So yeah, warm applause please for Nixo and Josh.
Hello, hello. Yes, it was a surprise announcement, and you guys are the first to hear, and we just submitted it. So we are super excited to announce that we're doing the first ever open internship at the EF in 2025. So the internship is going to be open to anyone. It's targeting university students, PhD students, and that's undergraduate students in like their third or fourth year, and really anyone who is looking to change their career or just has exceptional talent and wants to work in Ethereum. The teams that you will be able to work with at the EF internship are protocol security, the rig group, portal, testing, EOLs, Geth, account abstraction, and there's also a generalist role if there's something that is if you're very familiar with Ethereum and there's something very general and something very specific that you generally want to work with at Ethereum. Super excited. These are incredible teams to work with. All applicants will be paired with somebody at one of these teams, and they'll work closely for 3 months next summer, and it'll depend on whatever the schedule of the applicant is, and it'll start in June-ish 2025.
All right, thanks, Nick. So if you've been following the Ethereum Layer 1 development, you know that we have a few different sort of programs that target core developers. This program is not the protocol fellowship that has been going on for the past few years. This program is a little more targeted and guided through the process with the EPF. People who join fellows are able to work on the things that they want to work on. It's a lot more kind of free form and open, whereas this internship program, you'll be directly mentored by a single person who will kind of be giving you tasks to do and giving you a slightly more hand-holding through this process. In addition, it is a shorter duration, so yeah, there's that. We are going to be opening the applications tomorrow. So if you are interested in participating in this program, you can go to blog.ethereum.org, so the Ethereum blog, and you can see the blog post where there will be more details about this program as well as the link to the application form. Applications will be open until December 10th, but we will be parsing through these applications as they come in. So again, this is not yet public knowledge outside of Devcon, so you guys are all the first to hear it. If you're interested in participating, I would suggest getting your applications prepared ASAP because we will be looking through them as they do come in. And then, yeah, just share it with people who you feel like might be qualified. If you know about your local city or town's like blockchain organization or meetup group, and there are people that are you think might be interested in layer 1 development or getting into the space and have some computer science capabilities, please do share this announcement with them. Yeah, I think that's all.
Thank you so much. We're super excited to onboard the next cohort of developers and researchers.
Yep, thank you.
Thank you very much. Make sure to check them out and check all the internship programs, and thank you for coming. We'll be coming up with the next session, the evolution of ZK from 1985 to 2013 in a few minutes, so stay with us. Thank you. Hi everyone. So due to some unforeseen events, this session is cancelled. So the next topic that we'll have is on 3:10 p.m. We're going to talk about Circum buses, a new journey. So I'll see you at 3:10 p.m. Welcome back, everyone. I hope you had a great break and you're ready for the next session. As always, if you have any questions for the next speaker, we will have a QR code on the right. You can scan that, ask your questions, and also interact with the questions by upvoting them. So, without further ado, I would like to introduce the next speaker, Albert Rubio, who has been leading the development of Circum for the past 5 years. And in his next session, he will be talking about Circum Buses, a new journey. Please give him a big round of applause and welcome him on the stage.
everybody. I'm here to present a new great feature of Circum called buses. Okay, so just a little bit of context of what is Circum, just in case you don't know. So Circum is a DSL where the programmer explicitly provides the constraints defining the circuit and also provides an efficient way to compute the witness. In Circum, one of the nice features that we have a large library of circuits that programmers can reuse. And in fact, this is really encouraged because this is the best way to program easily good and safe new circuits. What the compiler does is, from this program, produces constraint system in R1CS on one hand, and on the other hand, you get the code that allows you to execute the circuit and compute the witness. So probably one of the drawbacks of Circum till today was the fact that Circum has or had a too simple type system. Okay, let's see it in an example. Assume that we want, just as a simple example, we want to build a circuit comparing dates. And then what happened that when you want to do that with Circum, there was no way to express dates. You just could include signals, and then you need to express 6 signals for day, month, and year of each of the inputs. Okay, so then you have something like this, which doesn't express any structure of the data as a date. Okay, so imagine that then you think, okay, let's put it all together, and then I use an array. But that's maybe even worse somehow, because you don't even have any clue about what's the day, what's the month, what's the year. So what do we really need? So what we need is doing it properly. Okay, and this is, from now on, can be done with buses. So with a bus, you can introduce this new type that says, well, this is a single structure that will have the day, the month, and the year. Okay, and then from that point on, you operate with this, and then you can say, well, I have 2 inputs that are dates, and then, of course, you can access these fields of the bus using the standard dot operation. Okay, so this looks much nicer. Okay, and so the point is that buses are a collection of signals, like structs in other languages. And of course, we call them buses because we work with circuits. And then what's a collection of signals? A bus. Okay, so this is the reason for the name and not using struct like in other languages. A bus can be defined in a very general way without restrictions. So you can use signals, arrays, and other buses, okay, all together. There is no restriction except for recursive definitions, but they will come soon. Okay, so then a bus defines a new type. And the point is that now using these types, the compiler can prevent from mixing data. And that's very important. Okay, so now we will be able to ensure type safety and so on. And also this will help us to define the library of circuits in a proper way, using all this data and make it this nicer. So let's see a bit of this orthogonality in the definition of the buses. And then you see here, I have this date, but then I can define a new bus that uses this bus, okay, inside an array. No restriction at all. So now we have a new bus definition, which is made of a signal and an array of dates. Okay. Look that also we can use parameterized buses as we can have parameterized templates in Circum. And this is just to make things fit well, because you see here I define a template with a parameter, and this parameter is used when defining a bus. Okay, so then I have this n for the template, and this n is again used to define the bus that I'm using as input. And look, then here I'm using an anonymous component, another feature of Circum. And you see, I'm just using as input the array of dates that was a field of this profile bus. Okay, so everything is done smoothly, like in any other language. Okay, so all of a sudden you can see this code, and it is no longer considered this low level. Okay, so it was something that was always said about Circum, that it was low level. It's not low level anymore. Okay, so look at this code. Doesn't look low level. So let's go a bit on what we are providing with this. So with now we can combine buses with another feature, what was called tags. And the combination of both things is that you get new types using buses, and then you also have some notion of subtyping using the tags. Okay? So know that now we can mix both things, the buses and tags. And then the tags can occur inside and outside the bus. So if they are inside the bus, they restrict any instance of this bus. So you attach this property to all instances of the bus. But if you use it outside, it's for the particular instance you're using. Okay, and adding tags is also very important, because somehow they show particular properties on the types. Okay, so this is a very nice combination that makes a good, still not so complex, but a strong and useful type system. Okay, so all this will impact a lot in the Circum lib, and let's see it through as an example coming from the library, which is this circuit for the baby jab elliptic curve. And then the point is that in the original form you have something like this. You see, you work with points, but what happens that you have again the points are not there. Okay, so you have here two signals, one for the x, one for the y, and each for the 2 points. So there is no structure here. And then you also have then operations for the Montgomery for the Montgomery form, and then we are using an array of 2 signals instead of the 2 signals. And then you see there is kind of a mismatch, but well, who cares? And then you have also the conversors as circuits, and then you see here we are using the Edwards forms here as 2 signals, and in the other part as an array of 2 signals. Okay, so altogether, okay, it's low readability and error prone. Okay, so what's different now? So look, I will just create a bus for Edwards point, and then I have all these so nicely written. Okay, I get an Edwards point, another point, and produce an Edwards point. Okay, so for Montgomery point, same there. Okay, I do this there, and I get the same nice presentation. And then for the, you see here, I have this 2 things, and now for the conversors, you see everything looks nice. And then we have readable code and type safe. Okay, so finally, using buses, I can avoid using both types of points, because in fact they are points, but the thing is that they are in one form or another. Then I use tags to distinguish them. You see here, I say, yeah, I have a point, but it's Edwards. Okay, and then in Montgomery, I say, I have a point, but it's Montgomery. Okay, and then with the conversion, it's clear that I go from a point in Edwards to a point in Montgomery. Okay, and then the type check will check everything. Okay, good. So we have revised the library. We have added buses, tags, make it compatible with different primes, and we don't need to audit again because we have formally verified that the constraints are the same. It's simply that they are nicely written. Okay. So conclusions, Circum is great, but now it's even better. Okay, so now we have these buses to structure secrets, and we can ensure type safety and increase readability and security and help audit all these ZK projects. And of course, we will have this new Circum lib for adapted to all this. And just this is for coming soon, but well, it's just what is coming in the next few months that will be useful for all developers. Okay, thank you very much.
Thank you very Thank you very much, Albert, for your wonderful presentation. Now for my favorite section, we're going to go to the Q&A. We have the QR code on the right. Make sure to scan it, and we can start with the first question. I saw a few questions kind of like are similar, so some people may be a bit confused about why a bus is called a bus, and why not struct or class?
As I said, because there is a circuit, we are programming circuits, and then buses is the word, I would say. It's not just, there is, I wouldn't say, well, you can call it a struct, because structs are in C-like languages, but then why not a map or a dictionary or so? So we decided, okay, we are doing circuits, so buses.
Got it, thank you. Now for the next question, are there any educational courses they can follow up to learn Circle programming language?
Oh, there are many. There is a lot of courses and tutorials and on the web for following and learning Circum. I think that if you just put the tutorials on Circum, you will get many of them available.
Gotcha. So put tutorials and you'll find a lot of resources and documentation on it.
Yeah.
Okay, next question is, what are some applications you're most excited about that is possible with Circum buses?
I mean, with buses, the point is not that you will be able to design new circuits. The point is that they will be defined in a nicer way, and they will be readable, and it will be much more difficult to make mistakes because even the compiler will check that all types match, and then you're not going to mix things that are not meaning the same. I think that it's more about the security of the circuits and of the way you program than the fact that you can develop new things or new projects that you could not do before.
Gotcha. So it improves the security, but also offers a better UX for the developers overall. Very nice. Will Circum become close to a high-level language like Python?
Well, in fact, as I said, I think that it already got with these new types and in the development. I think that this already can be considered a high-level language. Okay, maybe we don't have some of the features, but it's also because they are not needed for our purpose, I would say. I think that providing a good type system was the missing step for getting a high-level language.
Got it. We have a few more other questions, so people are very curious about Circum buses. So maybe when is it available to use?
It's already available. So the release was kind of a month ago, and we have just released the Circum 2.2.1 because we are fixing, we were improving some parts. But it's all available already, and you can download it and use it in all your circuits from now on. Okay? And for the Circum lib, it will be released, the new version with the buses will be released in few days. Okay?
Fantastic. So you can already try it out. Make sure to check it out. Is it possible to add methods or associated function to a bus?
Not this way, because this is not intended to be like this. I mean, we are not an object-oriented language, and the same as we don't have inheritance we just have this notion of subtyping by means of tags, and we are not considering that you have methods associated to templates. I mean, a template itself does. I mean, it's a sub-circuit, and it's not that much sense to add methods to do things on top of it. I mean, the circuit describes what is intended to do from the inputs to the outputs, but it makes no much sense to add new operations on top of it.
Got it. And I think this will be the last questions because we're running out of time. So tags don't have to be declared ahead of time. Seems like an easy way to make a typo.
Well, for types need to be declared ahead. So buses should be declared ahead before using them. But for tags, it's not like this. And well, maybe in the near future, maybe we will start at least to have the possibility to describe them and from the beginning associate them to some buses in advance to avoid mixing things or just making something that is not easy to read because you combine tags on different things, okay?
Fantastic. Well, thank you for answering these questions, and thank you for the audience for the questions. Again, a big round of applause for Albert, and thank you very much. Okay, I hope you're ready for the next session. We're going to look at the next session is C lookup, composite function-based lookup argument. So we will be in 5 minutes ready. Cool, welcome back. I hope you are all energized. We still have 2 more sessions left of this day, so we're almost done. I would like to introduce the next speaker, Wanso Blim, who will be talking about C lookup, composite function-based argument. I believe I pronounced that correctly, right? So he's been like advocating for open source fairness and a cypherpunk OG. So please give him a big round of applause and welcome him on the stage.
Hello, everyone. Thank you so much for coming to my talk. Today, I'm gonna have a talk about the C lookup, the lookup argument based on composite function. Actually, this is the first time ever that we are presenting our work. So my name is Wanso Blim and researcher at PSE. This is a joint work with my colleagues. So I did this work with Suwon and Do-hoon together. And the summary is that given that we have a n size of table and a witness with size of m, then if the witness size is much larger than the table size, we can accomplish a O of log squared m time complexity to the lookup argument. I'm going to explain more about how we achieve this. First of all, I would love to introduce where we got the inspirations. The first one was about the GKR, because we noticed that GKR is a one unique version of composite function. And the second was about Hyperplunk's PIOP2, the permutation argument PIOP2. It is also using kind of a composite function. It was very inspiring for me to think about the lookup argument using that. And so using that, we are using some composite function, just like in GKR's each layers. Actually, in our case, we are using only one layer, and we are achieving the O of log squared m time complexity. So first, let's discuss about the objective, and let's understand the current situation. That we have 2 sets. First one is about witness, and the second is about the elements of the given table. And our goal is to prove that for every element in W is also an element of a table. In other words, we are verifying that each witness element is contained within the table. And this implies that the set of witness W is a subset of the table T. Okay, and before we go deep dive into the lookup argument, C lookup argument protocol, I would love to introduce the main use case, the interesting use case, if we have the lookup argument. So what if we define each witness W as an encoding of function along with its input and output result? And let T be a predefined computations. Then we can formally verify that f of x equals to y always holds true, provided that the witness is a subset of the predefined computations. This means we can ensure that each computed value corresponds to a valid function and input and produces the correct output as specified in our predefined table of computations. And it becomes a cornerstone for formally verifiable computation. So we can implement some like ZK VM, which is also called the lookup singularity, which is also the jolt and lossless approach. So I'm going to introduce our approach, the C lookup approach. So first, we're going to define a relation, lookup, as the set of all tuples of public instance X and the witness W, where the public instance X is a tuple of oracles of functions F, T, and sigma, and the witness is a function of tuple of functions T, F, T, and sigma. To be precisely, F is a function that maps all the witnesses defined on a domain XF with range YF. And T is a function that maps table elements defined on a domain XT with range YT. Then if there exists a domain transformation function sigma that maps elements from XF to XT, also which satisfies that f of x equals to T of sigma of x for all the x in the domain XF. Then the range of F is a subset of the range of T. And we say that the tuple of public instance and witness is in the lookup relation. Okay. First, I'm going to show you the naive approach version. We'll consider a polynomial f and t and sigma over a finite field, and we're going to use univariate polynomial approach. Then we're going to map the witness and elements using the corresponding root of unity. And the relation that f of x always equals to T of sigma of x for all the roots of unity holds true if and only if there exists a quotient polynomial Q such that f of x minus T of sigma of x equals to z of x times Q of x for the vanishing polynomial z. Actually, here exists a caveat that the degree explodes. The degree explodes if we have the univariate polynomial and if we compute the composite function. The degree of the whole system becomes a degree of t times degree of the sigma. So which means like n times m. But if we use multivariate polynomial approach, it changes a lot. We will define the domain on the vector space. For the witness, we're going to define its domain as a Boolean hypercube over a log m dimensional space. And for the table, we're going to define the domain over the log n dimensional space. And then defining the domain transformation function sigma as a tuple of all the domain transformation functions, then the relation that the f of x always T of sigma of x holds true if and only if there exists a auxiliary polynomial h which satisfies some zero-check PIOP protocol. Precisely, here the R and R prime and gamma are the randomly chosen vector from the verifier, and the auxiliary polynomial gives us the relation that there exists mapping correctly, and the domain transformation is actually bound to the 0 and 1 correctly. As a result, we could achieve the log squared of m against the witness size, or log of the table size and complexity, time complexity. If we think about the protocol, let's go through the protocol quickly. So let's assume we have a witness witness vector f, and the table vector t, 2, 3, 5, 7, 11, 5, like blah, blah, blah. And the first step is preparation. So we're going to compute the table polynomial. But for a efficient some parallelization, we're going to use the coefficient form. But it doesn't, actually it does not a big thing, because it's a pre-processing period. And then we interpolate the witness. So just say for your easier understanding, I just expressed this in a coefficient form. And then we also need to find the domain transformation functions. This is just a mapping between the table domain, witness domain to the table domain. So if we express that in a coefficient form, actually we are using only the evaluation form. And then we use public coin protocol to run some check only once by patching everything together. So we choose, the verifier chooses the R prime, and gamma. And in this case, let's say we chose 31, 37 for R, and 5 and 7 for R prime, and 9 and 11, 13 for the gamma. We run some check. The first run will look like this. And you can see here, the intermediate univariate polynomial is not a linear function. It has some degrees. And we run the following round. And as a result, we need to check the resulting random evaluation from this sum check equals to the thing that we can query from the oracle, which was one of the public instance X. So we query the evaluations through the oracles, and we check this, the relation holds true by checking this condition and consistency. One important thing is that the main advantage of this approach is that it is very easy to decompose into smaller tables. So we have a T polynomial here, and we can decompose it into two smaller pieces, T1 and T2. In T1, it's just a T of 0, x2, x3. And T2 is actually T of 1, x2, x3. So we can decompose a table very easily. We can decompose more smaller pieces. Also, we can utilize this composite function approach with we can tweak a little bit. If we tweak this a little bit, then we can also compute the two intersection, size of two intersection of two given set. And actually, the result for the computational result also shows the same result. One of the key theses we had here is that if we use the composite function using multivariate setup, then the cost becomes too logarithmic. And if we maximize the parallelization, we thought that, okay, here's the composite function cost. And in univariate function, it was really high because the degree was exploding. But in multivariate setup, we can actually logarithmically change that. And the result is actually like, okay, it depends on the number of rounds times the composite function cost, evaluation of the composite function cost. And once again, composite function is a very, very generalized version of a GKR-ish approach. And to demonstrate our thesis, actually we implemented the CUDA-based sum-check protocol first in this repository. So it was a highly parallelizing all the evaluations, polynomial evaluations using GPU. And then we utilized this CUDA sum-check to see the results in this lookup repository. We just used KJJ just for easier implementation, but definitely you can change this commitment scheme to others. And successfully, we could see our result approach shows the logarithmic increase compared to the classical approach. Actually, the implementation and benchmark data is still being fleshed out. So, but we are pretty optimistic for about the result, that it's showing the sublinear result, not only against the witness side, but also against the table side. The conclusion. This approach is a very simple to understand, comparing to other lookup argument approach. And it supports table decomposition gracefully, and also it achieves sublinear proving time. My talk was a little bit longer than compared to the given time, so I cannot have some enough Q&A time. I'm going to be out there, so thank you so much for coming to my talk.
Thank you very much, Mansil, for your wonderful presentation and teaching us about C lookup. Thank you. And we're going to start at 3:50 with the last session. So stay tuned. We're going to start in a few minutes. Okay, so we are ready for the next and last session. So I hope you're all excited. Without further ado, I would just like to introduce the last speaker for stage 3, Hridam Basu, who is a cryptographic researcher at PSE. And for the next session, he will talk about Anon Aadhar, I believe I pronounced that correctly. So it's Anon Aadhar protocol using Noir 2 and Halo 2 and Noir. Please give him a big round of applause.
Hello everyone, my name is Hridam Basu and I'm going to be talking about Anon Aadhar protocol using Halo 2 and Noir. Without further ado, let's go into the talk. So here's a brief outline of the talk. I'll firstly introduce the protocol, what's the Anon Aadhar protocol, and then I'll go into the details of the circuit and the features and how you basically implement it, and then I'll go into the details of the implementations like Halo 2 and Noir, and then I'll end with applications. So the Anon Aadhar is basically a zero-knowledge proof of identity protocol for Indian citizens, which basically preserves the privacy and doesn't reveal the sensitive information which are there in any social security card. So the Aadhar is basically a social security card for Indians, and it also provides a set of tools for generating and verifying proofs, and it authenticates users and also verifies the proofs on chain. So there are a lot of problems with the previous proof of identity solutions, like in vanilla, KYC solutions. You need to reveal the full identity, and then if there is a centralized database like the Aadhar scheme, these databases are ideally vulnerable to database hacks and privacy leaks, and there was a lot of criticism for the Indian government since the time it came out. And of course, like if you put all this information on chain, it's also really bad. So there are a lot of other ways to do identity solutions. One is biometrics, where you can basically do like fingerprint scan or iris scan for creating immutable records. Also, there's a concept of an aggregation where you are basically combining activity data from various sources, and you can basically provide a comprehensive trust score, including some social graph analysis. And then there's the third category of leveraging document signatures, and this potentially uses some cryptographic signatures to verify and authenticate users on chain. So the Anon Aadhar protocol is in the last category and in the previous slide, and basically how we do it is basically we check both the SHA-256 hash and the RSA signature of Aadhar identity, and this basically was originally built at PSE with Circum. And there were 3 libraries. Basically, one was the TypeScript SDK, which is in the core repo, and then there's the Solidity library for the contracts, and also there's the React library. So what's the problem statement? So a government potentially will sign and issue an identity to a user or a citizen in this case, and the citizen basically gives this identity in the form of a scanner, we'll see in the next slide, to construct a proof, in this case a zero-knowledge proof, which will basically hide all the sensitive information, and then there's a verifier which verifies the proof of identity from the prover. So I think this audience is fairly knowledgeable about ZK snarks, but I'll briefly go over it for completeness. So ZK snarks are basically a way to prove the validity of a statement without revealing the witnesses or the private inputs. And S is the most important acronym, keyword in the acronym here. So succinctness, which means that it offers short proofs, and short verification time, which is basically ideal for on-chain verification. So and there are 2 properties, correctness and soundness, which basically means that it ensures proof validity and also prevents forgery. So this is a circuit. So in this part, basically it's the SHA and the RSA signature, which I described in the previous slide. Then there's the extracting the fields from the signed data. So the photo bytes are extracted, and it's used to compute the nullifier here. So along with a nullifier seed, which is also obtained as a public input here. And then there's the other part, which is the conversion of timestamp from IST timestamp to the UTC Unix timestamp, universal timestamp. And there's an algorithm for it. I'm not going to go into the details of it. And then there's the third part, which is the signal hash. So this is basically preventing front-running attacks. There's a constraint which we apply on the signal hash. So in the circuit, the private inputs are only the signature and the signed data. These are all public, and then this part is the conditional disclosure of secrets. So if these 4 parameters, there's 4 parameters in the Aadhar data, like age, gender, state, and PIN code. You can choose to reveal it. So if you choose to reveal it, then only these will be revealed at the end, right? So yeah, so basically this is the M-Aadhar app, where you can download the any Indian can download the like Aadhar card, or there's a scanner, and it hides all the sensitive information, and like these name, gender, and so on. And so these are the features of the Anon Aadhar protocol, like the user nullifier. This basically prevents double spending attacks, timestamp, this is acting as a time-based OTP system. The public key hash, it basically ensures that the signer's public key is same with the public key generated by the UIDAI, which is the authority, and also the signal hash, which is used to prevent front-running attacks. So I'll skip over the challenges and caveats, but mainly this says that there's a lot of problem with getting signed documents by the government and what kind of data the government chooses to sign. So Halo 2 is using Plonkish proof system and has a recursive proof support. So this is some of the libraries that I used for Halo 2, and I wrote each of the separate circuits that I shown in the circuit slide separately and combined them into one circuit and tested it with real data. So this is the results for Halo 2. So most of the stuff is very efficient in milliseconds for proving and microseconds and milliseconds for verification, except the RSA part. And the on-chain verification cost is also pretty efficient. It's like 6.5 million gas for the Halo 2 gas cost. And for Noir, it's one of the foremost proving systems by Aztec, and it basically, we can write custom circuits and prove a backend using Barrett-Inberg CLI. And same algorithm as Noir, like a Halo 2 implementation, elliptic curves and BN254, and the versions are given here. And these are the results for Noir, 0.5 seconds roughly for proving time for all of the parts of the circuit, and 0.05 seconds roughly for the verification time. The gas cost is like under 3 million for each of them. So the code is entirely open source. You can check it out. And in summary, Noir is much faster than Halo 2 in terms of all 3 parameters. Bottleneck in Halo 2 is RSA, but Circum, however, beats Noir and Halo 2 for on-chain verification cost. If you use Noir ultra honk backend, it's coming, so it might be more efficient. So there are lots of applications. I won't go into the details of it. Like, you can check it out in the Anon Aadhar page. So there's Privado ID, Semaphore, and Anon Aadhar check-in, and like quadratic funding, and lots of others. So these are some of the references, and I'll end here. Thank you so much for your attention, and I'll happy to take questions.
Well, thank you very much for presenting this. We can probably take one question from the audience. So maybe let's see, what are the plans to make it work in a real world local government office? Any ties up with the Indian government plan?
Yeah, this is a very good question. I actually am in the process of independently doing this work. So there can be lots of applications, and other government countries, of course, like there are other projects like Open Passport and like ZK Passport who are doing similar work, and I'm also in talks with them. So there is a plan to commercialize it, in short, but there is a lot of bureaucracy involved, particularly with the Indian government, if you talk about it. And with other governments, we can figure it out, but it's a separate thing from this, because PSE is, usually, not-for-profit organization. But yeah, I'll be happy to take this question offline, and if somebody is interested in the audience, we'll like to collaborate with them.
Sure, you guys know where to find him. So maybe we can take another question. So let's see, did you do the comparison between Noir and Halo 2 for benchmarking only, or they were complementary?
So yeah, I mean, not for, we did it for benchmarking with respect to Circum, because the original library is in Circum, and we implemented it because we wanted to understand if Halo 2 or Noir would be better in some aspects. Of course, Halo 2 had a steep learning curve, but Noir was really good. I mean, it's very easy to implement it, and also very efficient, and it depends on the details of implementation, but Noir is pretty good. Almost like Circum, but Circum still beats in terms of the gas cost today. Maybe in future, who knows, Noir might beat it.
Yeah, fantastic. I think we're running out of time, so do you want to take another one? Or
Sure, yeah.
Do you prefer something?
Yeah, isn't the on-chain address pseudonymous only? Yeah, I mean, the on-chain address is definitely I don't know the question, but generally, we can hide using ZK proofs all the information. So definitely, that's there.
Fantastic. Well, we're running out of time, so thank you, Freedom, again for your wonderful presentation. Please give him another round of applause. Thank you very much.
Thank you so much.
So we're kind of doing a wrap up. This was the last session for this stage. Make sure to join the closing ceremony at the main stage. It starts at 4:00 p.m. Thank you again for listening to me. My name is Robert Kodra. I'm a developer advocate at the Starknet Foundation, and I was the MC for today. Thank you again, and wishing you a nice day.
Is as much a technological object as it is a cultural object, right? It's not just technology, it's culture as well. And when you have something that has multiple dimensions, you can kind of like make different things load bearings at different times. If you have something that is purely technological and the technology doesn't work, then you have failed in some sense. You can kind of promise that it will work better at some point, but there's a thing where almost like a support network around you means you can take more risks. I think that having an object that has multiple dimensions makes it more anti-fragile in some sense. And so what I find really interesting with the Ethereum ecosystem is that in general, there's a lot of energy for things that on a surface level might look like playful or silly or not going anywhere. But actually, in many ways, I think this is almost like an immune system for making sure that excess talent and excess capital gets distributed to a lot of different kinds of experiments. Like one sentence we use as Zurich quite often is, when something is going in a strange direction or not successful, we say, that's an experiment worth enabling. Not like this is a failure or something like that. And I think the great thing with the Ethereum ecosystem is that it creates a lot of experiments worth being enabled. And you both kind of like increase your rate of trying things, but at the same time, you give a lot of space for things to grow. And one thing with cryptography, and we see it when we interface with academics or with the industry outside the Ethereum ecosystem, is that cryptography at this stage, outside what it can do very well and has been doing for many decades, it's almost like going back to square one in computing. And people don't want to go back to square one because they're like, I'm used to all of this nice stuff. Like, why would I go back to square one? And so in some ways, having a place where going back to square one actually has been done in recent memory, you know, like Ethereum has gone back to square one like a decade ago. So, because it started at square one. I think like this almost like knowledge, like it's still within this generation that this has happened, does create a lot of space.
Well, and going back to square one reminds me again of subtraction, so not to just completely hit this note again, but I think there's something important about being able to let go of things too. You know, I mean, there's this analogy that sometimes I bust out with people about ground apes, ground apes are really good at grabbing stuff. If a ground ape grabbed me, I'd be in trouble.